Hibernate Architecture. Here you can see a comprehensive architecture. The comprehensive architecture abstracts the application away from the underlying JDBC, JTA APIs and allows Hibernate to manage the details. Hibernate ORM, or simply Hibernate, is an object relational mapping tool for the Java programming language. It provides a framework for mapping an object-oriented domain model to a relational database. Hibernate handles object relational impedance mismatch problems by replacing direct persistent database accesses with high-level object handling functions. Here you can see a comprehensive architecture. The comprehensive architecture abstracts the application away from the underlying JDBC, JTA APIs and allows Hibernate to manage the details. Here are quick discussions about some of the APIs objects depicted in this diagram. SessionFactory, org.hibernate.sessionFactory, a thread-safe, immutable cache of compiled mappings for a single database. A factory for org.hibernate.session instances. A client of org.hibernate.connection.ConnectionProvider optionally maintains a second level cache of data that is reusable between transactions at the process or cluster level. Session, org.hibernate.session, a single-threaded short-lived object representing a conversation between the application and the persistent store, wraps a JDBC java.sql.connection, factory for Hibernate, Hibernate.transaction, maintains the first level cache of persistent the application persistent objects and collections. This cache is used when navigating the object graph or looking up object by identifier. Persistent objects and collections, short-lived single-threaded objects maintaining persistent state and business function. These can be ordinary Java beans, POJOs. They are associated with exactly one org.hibernate.session. Once the org.hibernate.session is closed, they will be detached and free to use in any application layer. For example, directly as data transfer objects to and from presentation. Transient and detached object and collections, instances of persistent classes that are not currently associated with org.hibernate.session. They may have been instantiated by the application and not yet persistent, or they may have been instantiated by a closed org.hibernate.session. Optional transaction org.hibernate.transaction. Optional, a single-threaded short-lived object used by application to specify atomic units of work. It abstracts the application from the underlying JDBC, JTA or COBA transaction. org.hibernate.session might span several org.hibernate.transactions in some cases. However, transaction demarcation either using the underlying API or org.hibernate.transaction is never optional. Connection provider, org.hibernate.connection.ConnectionProvider, optional, a factory for or pool of JDBC connections. It abstracts the application from underlying javax.sql.data source or java.sql.driver manager. It is not exposed to application, but it can be extended and or implemented by the developer. TransactionFactory, org.hibernate.TransactionFactory, optional, a factory for org.hibernate.transaction instances. It is not exposed to the application, but it can be extended and or implemented by the developer. Extension interfaces. Hibernate offers a range of optional extension interfaces you can implement to customize behavior of your persistent layer. Here you can see application. Inside the application, you can see transient objects. Persistent objects interacts with application and session. So below application you can see SessionFactory, TransactionFactory, ConnectionProvider, session and transaction. Below you can see JNDI, JDBC, JTA, and below that database. Here you can see a high level view of the Hibernate architecture. Here you can see application, persistent objects. You can see Hibernate, Hibernate.properties, and XML mappings are in Hibernate and database. Here we do not have the scope to provide more details view of all the runtime architectures available. Hibernate is flexible and supports several different approaches. We will, however, show the two extremes: minimal architecture and comprehensive architecture. Here you can see the minimal architecture. This diagram illustrates how Hibernate utilizes database and configuration data to provide persistent services and persistent object to the application. The minimal architecture has the application provide its own JDBC connections and manage its own transactions. This approach uses a minimal subset of Hibernate's APIs. Here you can see application. Transient objects are in application. You can see persistent objects and SessionFactory, session, JDBC, JNDI, JTA, and below database. Here you can see a comprehensive architecture. The comprehensive architecture abstracts the application away from the underlying JDBC JTA APIs and allow Hibernate to manage the details. Here you can see the roles of the most Hibernate interfaces important in the persistent and business layers of an application J2EE. The business layer is located on the persistence layer, since the business layer acts as a customer of the persistence layer. The interfaces shown can be classified as follows. Interfaces called by the application to perform basic operations, insertions, deletions, queries, etc. Session, transaction, and query interfaces called by the application infrastructure code to configure Hibernate. But the most important is the class configuration. Callback interfaces that allow the application to react to certain events that occur within the application, such as interceptor, lifecycle, and validatable. The interfaces that allow you to extend the mapping functionalities of Hibernate, for example, user type, composite user type, and identifier generator. Also, Hibernate makes use of Java APIs such as JDBC, JTA, Java Transform to TOPI, and Java Transaction API and JNDI, Java Naming Directory Interface. We will give you a brief review of some of the mentioned interfaces. The interface session is one of the primary interfaces in any Hibernate application. An instance of session, it is not very heavy, and its creation and destruction is very cheap. This is important as our application, you will need to create and destroy sessions all the time, maybe in every request. It may be helpful to think of a session as a cache or collection of objects loaded or from a database related to a single work unit. Hibernate can detect changes in objects belonging to a work unit. The interface SessionFactory allows you to get instances session. This interface is not light and should share among many threads of execution. Typically, there is one SessionFactory for entire application created during its initialization. However, if the application access to several databases, you will need a SessionFactory by each database. Interface configuration used to configure and start Hibernate. The application uses an instance of configuration to specify the location of documents, indicating the mappings of objects and specific properties of Hibernate, and then create the SessionFactory. The interface query allows requests to the database and control how that request is executed. Query requests are written in SQL or in the native SQL dialect of the database we are using. An instance query is used to link the parameters of the request, limit the number of results returned by the request, and to execute said request. Fundamental and very important element in Hibernate architecture is the notion of type. An object type Hibernate matches the Java type with a type of the column in the database. All persistent properties of persistent classes, including associations, they have a corresponding Hibernate type. Each design makes Hibernate highly flexible and extensible. Even user-defined types interfaces are allowed user type and composite user type. Session, transaction, query, SessionFactory configuration, inserts, interceptor, and user types are inside persistent layer. Interceptor and user type are connected to persistent classes. Lifecycle and persistent classes are connected to lifecycle and validatable. Lifecycle, validatable, and persistent classes are inside business layer. Business layer is connected to persistent layer. Here you can see below persistent layer JNDI, JDBC, and JTA. Here Hibernate APIs are lifecycle, validatable, session, transaction, query, SessionFactory, configuration, user type, and interceptor. Here J2E APIs are JNDI, JDBC, and JTA. Here you can see the architecture of Hibernate in another view. Hibernate as an ORM solution effectively sits between Java application data access layer and relational database, as can be seen in the diagram here. It sits between data access layer and the relational database. The Java application makes use of the Hibernate APIs to load, store, query, etc. in domain data. Here we will introduce the essential Hibernate APIs. Here you can see a data access layer is connected to Java persistent API and Hibernate native API. Java persistent API and Hibernate native API is connected to Hibernate, and interact with Hibernate. Hibernate interact with JDBC, and JDBC is connected to relational database. Here you can see Hibernate specific implementation. As a Jakarta persistent provider, Hibernate implements the Java persistent API specifications and association between Jakarta persistence interfaces and Hibernate specific implementation can be visualized in the following diagram. SessionFactory, org.hibernate.sessionfactory, a thread-safe and immutable representation of mapping of application domain model to a database, acts as a factory for org.hibernate.session instances. The entity manager factory is the Jakarta persistent equivalent of a SessionFactory, and basically those two converge into the same SessionFactory implementation. A SessionFactory is very expensive to create, so for any given database, the application should have only one associated SessionFactory. The SessionFactory maintains services that Hibernate uses across the sessions, such as second level caches, connection pools, transaction system integrations, etc. Session org.hibernate.session, a single threaded short-lived object conceptually modeling a unit of work. In Jakarta persistence nomenclature, the session is represented by the entity manager. The behind the scene, the Hibernate session wraps a JDBC java.sql.connection and act as a factory for org.hibernate.transaction instances. It maintains a generally repeatable read persistent context first level cache of the application domain model. Transaction org.hibernate.transaction, a single threaded short-lived object used by the application to demarcate individual physical transaction boundaries. Entity transaction is the Jakarta persistent equivalent and both act as an abstraction API to isolate the application from the underlying transaction system in use JDBC or JTA. Here you can see SessionFactory IMPL is connect. Here you can see SessionFactory IMPL class implement SessionFactory interface implement entity manager factory interface. Here's session IMPL class implement session interface implement entity manager interface. Here transaction IMPL class implement transaction interface implement entity transaction interface. Here you can see Hibernate architecture in a different view. Hibernate is a framework which is used to develop persistent logic which is independent of Hibernate software. In JDBC, to develop persistent logic, we deal with primitive types, whereas Hibernate frameworks, we use objects to develop persistent logic, which are independent database software. Here you can see Hibernate architecture. Configuration is a class which is represented in org.hibernate.cfg package. It activates Hibernate frameworks. It reads both configuration file and mapping files. Here you can see the sample code. It activates Hibernate framework here, and it read both CFG file and mapping files here. It checks whether the config file is syntactically correct or not. If the config file is if the config file is not valid, then it will throw an exception. If it is valid, then it creates metadata in memory and returns the metadata to object to represent config file. SessionFactory. SessionFactory is an instance which is represented in org.hibernate package. It is used to create session object. It is immutable and thread safe in nature. Here the built SessionFactory method gathers the metadata which is in the CFG object. From CFG object, it makes a JDBC information and create a JDBC connection. Session is an interface which is represented in the org.hibernate package. Session object is created based upon the SessionFactory object, that is factory. It opens the connection session with database software through Hibernate framework. It is a lightweight object and it is not thread safe. Session object is used to perform CRUD operations. Transaction object is used whenever we perform any operation and based upon that operation there is some change in the database. Transaction object is used to give that instruction to the database to make the changes that happen because of the operation as a permanent by using a commit method. Query is an interface that represents inside org.hibernate package. Query instance is obtained by calling session.createFactory method. This interface exposes some extra functionality beyond that provided by session.iterate and session.find methods. First, a particular page of the result set may be selected by calling setMaxResult method and setFirstResult method. Two named query parameters may be used. Criteria is a simplified API for retrieving entities by exposing criterion objects. A session is a factory for criteria. Criterion instances are usually obtained via the factory methods on restrictions. Here you can see configuration is connected to mapping information via add annotation method. Here configuration is connected to DB information via configure method. Here configuration is connected to SessionFactory via build SessionFactory method. SessionFactory is connected to session via open session method. Session is connected to transaction via begin transaction method. Here session is connected to query via create query method. Session is connected to criteria via create criteria method. Here you can see a working flow of Hibernate framework to save and retrieve data from the database in form of object. Suppose we want flow of working during operation in Hibernate framework. Suppose we want to insert an object to the database. Here object is nothing but persistent logic which we write on Java program and create an object of that program. If we want to insert an object in the database, so we want to retrieve the object from the database. Now the question is that how Hibernate save the object to the database or retrieve the object from the database. There are several layers through which Hibernate framework go to achieve the above task. Let us understand the layers flow of Hibernate framework during performing operations. Stage 1. In the first stage, we will write the persistent logic to the database with the help of Hibernate configuration file and Hibernate mapping file, and after that we create an object of a particular class on which we wrote the persistent logic. Stage 2. In the second stage, our class which contains the persistent logic will interact with the Hibernate framework where Hibernate framework gives some abstraction, do perform some tasks. Now here the picture of Java class is over. Now Hibernate is responsible to perform the persistent logic with the help of layers which is below Hibernate framework, or we can say that layers which are in the internal implementation of Hibernate. Stage 3. In third stage, our Hibernate framework interact with JDBC, JNDI, JTA, etc. to go to the database to perform that persistence logic. Stage 4 and 5. In fourth and fifth stage, Hibernate interact with database with the help of JDBC driver. Now here Hibernate perform that persistent logic which is nothing but CRUD operation. If our persistent logic is to retrieve and record, then the reverse order it will display on the console of our Java program in terms of object. Here you can see object-based OR mapping persistent logic. Inside it you can see HB CFG file, entity class, and HB mapping file. Object-based OR mapping persistent logic is connected to object. Object is connected to Hibernate framework here, and basically object-based OR mapping persistent logic interacts with Hibernate framework through objects. Hibernate frameworks interact with JDBC, JNDI, JTA. JDBC, JNDI, JTA interacts with JDBC driver. JDBC driver interacts with database. Here object-based OR mapping persistent logic is connected to object. Object is connected to Hibernate framework. Hibernate framework is connected to JDBC, JNDI, or JTA. Those are connected to JDBC driver. JDBC driver is connected to database. And the other way, database is connected to JDBC driver. JDBC driver is connected to JDBC, JNDI, or JTA, and those are connected to Hibernate framework. Hibernate framework is connected to object. Object is connected to object-based OR mapping persistent logic. Here you can see a Hibernate architecture in a different view. As you can see from this picture, how much of Hibernate you use depends on your needs, and its simplest level, Hibernate provides the lightweight architecture that deals only with ORM. Full-blown usage of Hibernate fully abstract most aspect of persistence, such as transaction, entity query caching, and connection pooling. Here you can see application. Inside it you can see transient POJOs. Persistent POJOs interacts with application and Hibernate. Inside Hibernate you can see SessionFactory, session transaction connection, TransactionFactory, and ConnectionProvider. Persistent POJOs access session and session access persistent POJOs. SessionFactory create session, TransactionFactory create transaction, ConnectionProvider creates connection. Below you can see J2E, JDBC, JCA, JNDI, JMX, and JTA are inside J2E. Transient POJOs, persistent POJOs, SessionFactory, and JDBC are in lightweight architecture. TransactionFactory, transaction, ConnectionProvider, connection, JCA, JNDI, JMX, and JTA are in fully integrated architecture. Here you can see how Hibernate works. The Hibernate success lies in the simplicity of its core concept. At the heart of every interaction between your code and the database lies in the Hibernate session. This image provides an overview of how Hibernate works and don't need any explanation if you have an idea about Hibernate. The heart of any Hibernate application is its configuration. There are two pieces of configuration required in any Hibernate application. One creates the database connections, and the other creates object to table mapping. Let's see the basic introduction to all the component and the roles in Hibernate. Configure the Hibernate connection .cfg.xml. To create connection to the database, Hibernate must know the details of the details of our database, tables, classes, and other mechanics. This information is ideally provided with an XML file, usually named hibernate.cfg.xml, or as simple text file with the name value pairs, usually named hibernate.properties. In XML style, we name this hibernate.cfg.xml we name this file hibernate.cfg.xml so the framework can load the file automatically. And create mapping definitions. Once we have connection configuration ready, next step is to prepare table1.hbm.xml file consisting of Hibernate table mapping definitions. There's a lot going on mapping files. The Hibernate mapping element hold all the classes to the table mapping definitions, etc. So what does Hibernate do with these properties files? And the Hibernate framework loads this file to create a SessionFactory, which is thread safe global factory class for creating sessions. We should ideally create a single SessionFactory and share it across the application. Note that the SessionFactory is defined for one and only one database. For instance, if you have another database alongside MySQL, you should define relevant configuration in hibernate.hbm.xml to create separate SessionFactory for that database too. The goal of the SessionFactory is to create session objects. Session is a gateway to our database. It is the session's jobs to take care of all database operations such as saving, loading and retrieving records from relevant tables. The framework also maintains a transactional transactional medium around our application. The operations involving on the database across access we wrapped up in a single unit of work called transaction. So all the operations that transaction are either successful or rolled back. Keep in mind that the configuration is used to create session via a SessionFactory instance. Before we moved on, note that the session objects are not thread safe and therefore should not be shared across different classes. The Hibernate session embodies the concept of a persistent service or persistence manager that can be used to query and perform insert, update and delete operations on instances of class mapped by Hibernate. In an ORM tool, you perform all of these interactions using object-oriented semantics. That is, you no longer are referring to tables and columns, but you use the classes and object properties. As its name implies, the session is a short-lived lightweight object used as a bridge during a conversation between the application and the database. The session wraps the underlying JDBC connector or J2E data source, and it serves as first cache for persistent object bound to it. SessionFactory. Hibernate requires that you provide it with the information required to connect each database being used by the application, as well as which classes are mapped to the given database. Each one of these database specific configuration files along with the associated class mappings are compiled and cached by the SessionFactory, which is used to retrieve Hibernate sessions. The SessionFactory is a heavyweight object that should ideally be created only once, since it is an expensive and slow operation and made available to the application code that needs to perform persistence operations. Each SessionFactory is configured to work with a certain database performed by using and provided Hibernate dialects. The choice of Hibernate dialect is important when it's come to using database specific features like native primary key generation schemes or session locking. At the time of the writing, here we are considering version 3.1 supports 2.22 database dialects. Each of the dialects implementations are in the package org.hibernate.dialect. Hibernate object mappings. Hibernate specifies how each object state is retrieved and stored in a database via an XML configuration file. Hibernate mappings are loaded at startup and are cached in the SessionFactory. Each mapping specifies a variety of parameters related to the persistent lifecycle of instance of the mapped class, such as primary key mapping and generation scheme, object field to table column mapping, associations, collections, caching settings, custom SQL, store procedure calls, filters, parameterized queries, and more. Here you can see .csv.xml here loaded to create Hibernate configuration for database 1 here. Hibernate configuration for database 1 is connected to database 1 here. Here .csv.xml defines database specific settings and groups HBMs for given database. .cfg.xml is connected to here class 1.hmb.xml, class 2.hmb.xml, etc. Here the .cfg.xml is connected loaded to create Hibernate configuration for database 2, and Hibernate configuration to the database 2 is connected to database 2 database 2 work with multiple here databases. Hibernate configuration for database 2 is connected to basically here Hibernate configuration object is used to create factory here singleton per database. Factory is connected to session interacts with the tables and classes via bridge. Here you can see Hibernate ORM and Hibernate OGM. For example, instead of using JPA repository, you will use MongoDB repository. MongoDB does not require following ACID properties and hence do not support transaction. Hibernate OGM mitigates its lacking by queuing changes before committing them. Hibernate OGM also recommends using transaction demarcation with no rollback option. Perhaps this is the reason why bootstrapping through JDBC is suggested. Because of JPA is an inherently relational API, so we prepared for you to run into this aspect. JPA is not supporting a plethora of features MongoDB exposes, geospatial functionality, upserts, etc. We are going to need to custom extensions for which minimizes benefit of using JPA in the first place. A plethora of stuff available in JPA doesn't make any sense in MongoDB non-relational world and won't be supported transactions. What's a join column supposed to be in MongoDB, etc. 3. Simplicity. Simply switching the store behind an object is fallacy 2. Here you can see the Hibernate ORM. Database interacts with JNDI or JDBC layer or JTA. JNDI or JDBC layer, JTAs and SQL statement are connected to SQL database via SQL statement, and SQL database is connected to JT or JNDI or JDBC layer or JTA via results. And next you can see Hibernate ORM and then application. Hibernate, here you can see Hibernate OGM. NoSQL database interacts with data store provider or grid dialect. Then you can see Hibernate OGM, then Hibernate ORM, then application. Here you can see general architecture of Hibernate OGM. Hibernate OGM is made possible by the reuse of a few key components. Hibernate ORM for JPA support. The NoSQL drivers to interact with the underlying data store. Optionally, Hibernate search for indexing and query purposes. Optionally, InfiniSpan's Lucene directory to store indexes in the InfiniSpan itself, or many other NoSQL using InfiniSpan's wire through cache stores. Hibernate OGM itself. Hibernate OGM reuses as much as possible from the Hibernate ORM infrastructure. There is no need to rewrite a new JPA engine. The persister and the loaders, two interfaces used by Hibernate ORM, have been written to persist data in the NoSQL store. These implementations are the core Hibernate OGM. The particularities between NoSQL stores are abstracted by the notion of a data store provider and grid dialect. Data store provider abstract how to start and maintain the connection between Hibernate OGM and data store. Grid dialect abstract how data itself, including associations, are persisted. Think of them as JDBC layer for our NoSQL stores. Other than this, all the create, read, update, delete CRUD operations are implemented by the Hibernate ORM engine, object hydration and dehydration, cascading, life cycle, etc. As of today, we have implemented following data store providers: a hashmap based data store provider for testing, and InfiniSpan embedded data store provider for persist your entities in an InfiniSpan instance running within the same JVM, and InfiniSpan remote data store provider to persist your entities in InfiniSpan over a remote hot rod client, and EHCache based data store provider to persist your entities in EHCache, a MongoDB based data store provider to persist data in a MongoDB database, a Neo4j based data store provider to persist data in a Neo4j graph database, a CouchDB based data store provider to persist data in a CouchDB document store experimental, a Cassandra based data store provider to persist data in Apache Cassandra experimental, a Redis based data store provider to persist data in the Redis key value store experimental, an Ignite based data store provider to persist data in the Apache Ignite experimental. To implement JPQL queries, Hibernate OGM passes the JPQL string and calls then the appropriate translator functions to build a native query. Since not all NoSQL technologies support querying, when lacking, we can use Hibernate search as an external query engine. Hibernate OGM best works in a JTA environment. The easiest solution is to deploy it on a Java EE container. Alternatively, you can use the standalone JTA transaction manager. Here you can see object model is inside application. Application interacts with JPA or Hibernate native APIs. JPA or Hibernate native APIs, Hibernate OGM core, Hibernate ORM core, data store provider and grid dialect. and query engine are inside Hibernate OGM. JPA or Hibernate Native API interact with Hibernate ORM core. Hibernate ORM core delegate persistence load queries to Hibernate OGM core. Hibernate OGM core delegates data store CRUD operations to data store provider and grid dialect. Data store provider and grid dialect interacts with data store. Here Hibernate OGM core delegates queries to JPQL parser. JPQL parser and data store query translator are inside query engine. JPQL parser delegates queries to data store query translator. Data store query translator execute native queries execute native queries, and data store query translator is connected to NoSQL data store via execute native queries. Now we are considering using Hibernate search as a query engine. Grayed areas are blocks already present in Hibernate OGM architecture. Since Hibernate OGM, how is data queried? Since Hibernate OGM wants to offer all of JPA, it needs support for JPQL queries. Hibernate OGM passes the JPQL query string and extract its meaning. From there, several options are available depending on the capabilities of the NoSQL data store you target. It directly delegates the native query generation to the data store specific query translator implementation. It uses Hibernate search as a query engine to execute the query. If no SQL data store has, if the NoSQL data store has some query capabilities, and if JPQL query is simple enough to be executed by the data store, then JPQL parser directly pushes the query generation to the NoSQL specific query translator. The query returns the list of matching entity columns and projections, and Hibernate OGM returns managed entities. Some NoSQL stores has a poor query support or none at all. In this case, Hibernate OGM can use Hibernate search as its indexing and query engine. Hibernate search is able to index and query objects, entities, and run full text queries. It uses well-known Apache Lucene to do this, but adds a few interesting characteristics like clustering support and an object-oriented abstraction, including an object-oriented query DSL. Let's have a look at the architecture of Hibernate OGM when using Hibernate search. In this situation, Hibernate ORM core pushes change events to Hibernate search, which will index entries accordingly and keep the index and the data store sync. The JPQL query parser delegates the query translation to the Hibernate search query translator. And executes the query on top of the Lucene indexes. Indexes can be stored in various fashions: on a file system, the default in Lucene; in InfiniSpam via the InfiniSpam Lucene directory implementation. The index is then distributed across several servers transparently. In NoSQL stores that can natively store Lucene indexes. In NoSQL stores that can be used as overflow to InfiniSpan. In this case, InfiniSpan is used as an intermediary layer to serve the index efficiently but persist the index in another NoSQL store. You can use Hibernate search even if you do plan to use the NoSQL data store query capabilities. Hibernate search offers a few interesting options clusterability, full text queries, that is Google for your entities, geospatial queries, query faceting, that is dynamic categorization of the query result by price, brand, etc. Here you can see object, you can see application interacts with JPA or Hibernate native API. Here Hibernate search and index, Hibernate search indexing engine and query engine and other components are inside Hibernate OGM. Here JPA or Hibernate native APIs interacts with Hibernate ORM core. Hibernate ORM core delegate persistence load queries to Hibernate OGM core. Hibernate OGM core delegates queries to JPQL parser. JPQL parser delegates simple queries to Hibernate search query engine. The JPQL parser and Hibernate search query engine are inside query engine. Hibernate search query engine reads Lucene indexes. Here Hibernate ORM core sends entity change event to Hibernate search indexing engine. Application is connected to Hibernate search indexing engine. Hibernate search indexing engine writes Lucene indexes. Lucene indexes optionally store in NoSQL data store. Here you can see Hibernate's two-level cache. Hibernate has two-level cache architecture. First level cache and second level cache. First level cache is the persistent context cache scope of a session. The cache ensures that when the application requests the same persistent object twice in a particular session, it gets back the same identical Java instance. Moreover, all entity instances handled in a particular unit work. Particularly Hibernate does not share cache between threads. Each application thread has its own copy of the data in cache. As a result, this prevents issue with translation isolation as well as concurrency once accessing the cache. Second level cache is a process or cluster scope in the JVM scope of SessionFactory. Multiple application threads may access the shared second level caches concurrently. The second level cache is very useful for reducing read-write transaction response time, especially in master-slave replication architectures. Here you can see thread interacts with the second level via persistent contexts. Here persistent contexts and threads are in first level. Here persistent context interacts with thread here. Cache concurrency strategy, query result cache and cache provider. Here you can see cache regions are in second level. Entity data, connection element and natural identifier are in cache concurrency strategy. Cache you can see cache provider behind cache concurrent strategy and query result cache. Cache provider is connected to cache regions, and here first level and second level are in a JVM. Here cache provider interacts with another cache provider in another JVM, and that cache provider interacts with another cache provider in another JVM. JVMs interacts with the database here. Now we are here. You can see Hibernate second level cache. Hibernate second level cache is one of the data caches component available in the Hibernate Object Relational Mapping ORM library. Hibernate is a popular ORM library for Java language, and it lets you store your Java object data in a relational management system, RDBMS. Since Java objects do not naturally align with the tables, rows, columns of an RDBMS, a phenomenon known as impedance mismatch, Hibernate acts as a translation layer. With Hibernate, you can easily and quickly access relational data by providing mapping mechanisms from relational database tables, rows, columns, and foreign keys to your annotated Java classes. Hibernate generates SQL queries with an easy to use syntax to query data based on Java object oriented domain model. The second level cache is enabled by plugging the third party caching technology to expand built-in caching capabilities in Hibernate. It is used to overcome the limitations of first level cache described now. Caching is one of the strength of Hibernate framework. It is available in multiple levels. First level caching is the first place that Hibernate checks for cached data. It is built in and active by default to reduce a number of SQL queries directly to the database. If the requested query results are not in the first level cache, then queries run against the underlying database, that is, if there is no second level cache enabled. This cache only works at session level, meaning each session object caches data independently, so there is no sharing of cache data across sessions, and the cache data is deleted when session closes. This makes the cache only useful for repeated queries in the same session. For repeated queries across multiple sessions, that's where the second level cache comes into play. With Hibernate second level cache, you can plug in caching technology to component the first level cache to complement the first level cache. If the requested query results are not in the first level cache, then the second level cache is checked. The second level cache shares cache data across sessions, so all sessions users can benefit from the cache data, even for data that was inserted by another session, and even if the session that inserted the data into the second level cache closes. Why is the second level cache important for Hibernate? The second level cache improves the application performance with regards to persistence for all sessions created with SessionFactory. Within second level cache, a request for an object can be served by the cache even if the request is executed from multiple sessions with much lower latency than if the request went through the database. Considering the ROM queries can be complex and therefore relatively slow, a system can greatly benefit from second level cache to reduce the repetition of the same complex or slow queries to the underlying database. This is specifically useful for high volume web applications that have commonly across users in terms of SQL queries to the database. And with high scalable caches, you can cache more data and realize more performance acceleration. What can be used as a Hibernate second level cache? Any technology that supports out-of-box integration with Hibernate can be plugged in to act as a second level cache. In-memory data grids are commonly used as Hibernate second level cache. For example, Hazelcast IMDG has built-in integration with Hibernate to easily plug in for second level caching. With its distributed architecture, you can add more nodes to the cluster to grow cache as much as you want to handle heavier workload. Here a client is connected to session. SessionFactory and first level cache are inside Hibernate. Session is connected to first level cache and first level cache is connected to database. Session is connected to SessionFactory. SessionFactory is connected to second level cache. Second level cache is inside ConnectionProvider. Here you can see a big picture of entity types versus value types. To understand the behavior of various Java language level objects with respect to persistent service, Hibernate classify them into two groups, entity types and two value types. Entity types if an object has its own database identity, a primary key value, then its type is entity type. An entity an entity has its own life cycle. It may exist independently of any other entity. An entity reference to an entity instance is persistent as a reference to the database, a foreign key value. From this picture, the college is an entity type. It has its own database identity. It has a primary key. Value types. If an object does not have its own database identity, no primary key value, then its type is a value type. Value type objects belongs to an entity type object. It's embedded in the owning of entity and represent the table column in the database. Lifespan of a value type instance is bounded by lifespan of the owning entity instance. Basic value types. Basic value types are they map a single database value column to a single non-aggregated data type. Hibernate provides number of built-in data types. string, character, boolean, integer, long, byte, java.sql date, java.net.url, java.sql.blob, java.util.uuid, etc. are built-in basic value types. You can find all basic types in Hibernate documentation, basic value types. Composite type, value types, embeddable types. In JPA, composite types are also called embedded types. Hibernate traditionally called them components. Composite value types look like exactly an entity, but does not own lifecycle and identifier. Mapping composite value, you can see collection value types. Hibernate allows to persist collections. Collection value types subcategorize into 3 types: collection of basic value types, collection of composite or embeddable types, collection of custom types. Here you can see Hibernate as 2 types: entity types and value types. Entity types: an object of entity types has its own identity, primary key value. An entity has its own life cycle. Value types: an object of value types has no database identity, no primary key. It belongs to an entity and it is embeddable in a table row of owning entity, table column. Entity type has basic types, composite types and collection types. Basic types you can see here, and composite types here, and collection types here, and here the mapping we will here you can see. Here you can see Hibernate life cycle. Here we will learn about Hibernate's life cycle, or in other words we can say that we will learn about the life cycle of mapped instances of the entity object classes in Hibernate. In Hibernate we can either create a new object of an entity and store it into the database, or we can fetch the existing data of an entity from database. This entity is connected with the lifecycle, and each object of entity passes through the various stages of the lifecycle. There are mainly 4 stages of the Hibernate lifecycle: 1 transient state, 2 persistent state, 3 detached state, 4 removed state. As depicted from this media, one can collocate how they are plotted in order to plot better in our mind. Now we will be discussing the stages to better interpret Hibernate lifecycle. It is as follows. Stage 1, transient state. The transient state is the first state of an entity object. When we instantiate an object of a POJO class using the new operator, then the object is in the transient state. This object is not connected with any Hibernate session. So this state is not connected to any database table. So if we make any changes in the data of the POJO class, then the database table is not altered. Transient objects are independent of Hibernate and they exist in the heap memory. there are two layouts in which transient state will occur as follows. One, when objects are generated by an application but are not connected to any session. Two, the objects are generated by a closed session. Here we are creating a new object for the employee class. The code, this is the code which shows initialization of an employee object. Here the object arrives in the transient state. Now we are considering a persistent state. Once the object is connected with the Hibernate session, then the object moves into persistent state. So there are two ways to convert the transient state to the persistent state. One, using hibernated session, save the entity object into the database table. Two, using hibernated session, load the entity object into the database table. In this state, each object represents one row in the database table. Therefore, if we make any changes in the data, then Hibernate will detect these changes and make changes in the database table. Following are the methods given for the persistent state. Session.persist e, session.save e, here, session.save or update e, session.update e, session.merge e, here session.merge e, and session.lock e. Here you can see transient state, and now it's to here you can see persistent state. State 3, detached state. For converting an object from persistent state to detached state, we either have to close the session or we have to clear its cache. As the session is closed here, or the cache is cleared, then any changes made to the data will not affect the database table. Whenever needed, the detached object can be reconnect to a new Hibernate session. To reconnect the detached object to a new Hibernate session, we will use the following methods as follows. Merge, update, load, refresh, save, and save or update. The following are the methods used for the detached state. Session.detach e, session.evict e, session.clear, session.close. Here the transient state, here persistent state, here detached state, state 4 removed state. In the Hibernate life cycle, it is the last state. In the removed state, when the entity object is deleted from the database, then the entity object is known to be in the removed state. It is done by calling a delete operation. As entity object is in the removed state, if any change will be done in the data will not affect the database table. Not to make a removed entity object, we will call session.delete. Here the Java pseudocode to illustrate remove state. Here transient state. Here persistent state. Here removed state. Here transient new via new instant of entity, it is connected to transient state, and transient state is connected to persistent state via save method, persist method, save update method, and update method. Via get method and load method, it is connected to persistent state. Persistent state interact with detached state. Persistent state is connected to detached state via detach method, close method, clear method, evict and evict method. Here detached state is connected to persistent state via save method, save update method, merge method, and lock method here. And detached state is connected to end here via garbage, and transient state is connected to end here via garbage. Persistent state is connected to removed state via delete method. Remove state state is connected to the end via garbage. Here you can see a directory structure in a project Hibernate XML configuration example with the Maven plus Eclipse plus MySQL database. Here you can see JPA entity. Here configure SessionFactory. Here define Hibernate database configuration. Here you can see Hibernate hello world example, and under that settings src and target.classpath.project and pom.xml. Here under src you can see main, under main main and test. Under main you can see Java and resources. Under Java you can see net, and under net you can see Java guides. Under Java guide you can see the folder directory Hibernate. Under Hibernate there are two subdirectories, entity and util, under and app.java here. Under entity here student.java jpa entity, and under util Hibernate util.java configure SessionFactory. Under resources you can see file hibernate.cfg.xml defines Hibernate database configuration. Under test you can see two directories, Java and resources. Now we are focusing on application. Application software is programs designed to handle specific tasks for users. Smartphone apps became a common way for individuals to access information systems. Other examples include general purpose application suites with their spreadsheet and word processing programs, as well as vertical applications that serve a specific industry segment. For instance, an application that schedules, routes and tracks package deliveries for an overnight carrier. Larger firms use licensed applications developed and maintained by specialized software companies, customizing them to meet their specific needs, and develop other applications in-house or on an outsourced basis. Companies may also use applications delivered as software as a service SaaS from the clouds over the web. Proprietary software available from and supported by its vendors is being challenged by open source software available on the web for free use and modification under a license that protects its future availability. Here you can see Spring MVC plus Spring Data JPA plus Hibernate, crude example here. Now we are focusing on transient objects. An object is transient if it has just been instantiated using the new operator and it is not associated with a Hibernate session. It has no persistent representation in the database and no identifier value has been assigned. Transient instances will be destroyed by the garbage collector if the application does not hold a reference anymore. Use the Hibernate session to make an object persistent and let Hibernate take care of the SQL statements that need to be executed for this transaction. Here you can see changing new objects to transient state. Transient state is the first state of an entity object. When we instantiate an object of Pojo class using a new operator, then the object is in the transient state. This object is not connected with any Hibernate session. As it is not connected to any Hibernate session, so this state is not connected to any database table. So if we make any changes in the data of the Pojo class, then the database table is not altered. Transient objects are independent of Hibernate and they exist in the heap memory. There are two layouts in which transient state will occur as follows. One, when objects are generated by an application but are not connected to any session. The objects are generated by a closed session. Here you can see a transient. Transient entities exist in heap memory as normal Java objects. Hibernate does not manage transient entities. The persistent context does not track the changes done to them. In simple words, a transient entity has neither any representation in the database nor in the current session. A transient entity is simply a POCHO without any identifier. Here you can see transient employee entity here. Here POCHO interacts with the client. Additionally, we are considering here detached objects. Detached objects exist in the database but are not maintained by Hibernate. Detached entities have a representation in the database, but these are currently not managed by the session. Any changes to a detached entity will not be reflected in the database and vice versa. A detached entity can be created by closing the session that was associated with, or by evicting it from the session with the call to the session's evict method. Here you can see detaching an entity from session. Here, this temporary separation of the entity and database is shown in this image here. One reason you might consider doing this would be read an object out of the database, modify the properties of the object in memory, and then restore the result someplace other than your database. This would be an alternative to doing a deep copy of the object. Note that in order to make a persistent entity from detached entity, the application must reattach it to a valid Hibernate session. A detached instance can be associated with a new Hibernate session when new application calls one of the load method, refresh method, merge method, update method, or save methods on the new session with a reference to the detached object. After the method called, the detached entity would be a persistent entity managed by a new Hibernate session. Here POCHO interact with client. Here database interact with POCHO table. As an example, you can see this code segment. Here we are creating a new object for the employee class. Here is the code which shows initialization of employee object. Here the objects arrived in the transient state. As an example too, we are considering at transient Jakarta persistent annotations in mapping annotations. The at transient annotation is used to specify that a given entity attribute should not be persisted. The annotation type transient specified that the property or field is not persistent. It is used to annotate the property or field of an entity class mapped superclass or embeddable class. This is with regarding transient fields. As an exception example, we can consider transient object exception thrown when the user passes a transient instance to a session method that expects a persistent instance. This exception is in org.hibernate package. As an error example, we can consider this object references an unsaved transient state, unsaved transient instance. Now we are focusing on persistent objects. A persistent instance has a representation in the database and an identifier value. It might just have been saved or loaded. However, it is by definition in the scope of a session. Hibernate will detect any changes made to an object in persistent state and synchronize the state with the database when the unit of work completes. Developers do not execute manual update statements or delete statements when an object should be made transient. Here you can see Hibernate life cycle. Here we will talk about Hibernate lifecycle, or in other words, we can say that we can talk about the lifecycle of the mapped instances of the entity object classes in Hibernate. In Hibernate, we can either create a new object of an entity and store it into the database, or we can fetch the existing data of an entity from the database. This entity is connected with the lifecycle, and each object of entity passes through the various stages of the lifecycle. There are mainly 4 states of the Hibernate lifecycle: transient state, persistent state, detached state, removed state. The transient state is the first state of an entity object. When we instantiate an object of Pojo class using the new operator, then the object is in the transient state. This object is not connected with any Hibernate session. As it is not connected to any Hibernate session, so this state is not connected to any database table. So if we make any changes in the data of the Pojo class, then the database table is not altered. Transient objects are independent of Hibernate and they exist in the heap memory. There are 2 layouts in which transient state will occur as follows. One, when objects are generated by an application but are not connected to any session. 2. The objects are generated by a closed session. Persistent state. Once an object is connected with the Hibernate session, then the object moves into the persistent state. So there are two ways to convert the transient state to the persistent state. One, using Hibernate session, save the entity object into the database table. 2, using the Hibernate session, load the entity object into the database table. Following are the methods given for the persistent state. Session.persist, session.save, session.save or update, session.merge, session.lock. Detached state. For converting an object from persistent state to detached state, we either have to close the session or we have to clear its cache. As the session is closed here or the cache is cleared, then any changes made to the data will not affect the database table. Whenever needed, the detached object can be reconnected to a new Hibernate session. To reconnect the detached object to a new Hibernate session, we will use following methods as follows: merge, update, load, refresh, save, following are the methods used for the detached state. Session.detach, session.evict, session.clear, session.close. Removed state. In Hibernate lifecycle, it is last state. The removed state when the entity object is deleted from the database, then the entity object is known to be in the removed state. It is done by calling delete operation. As the entity object is in the removed state, if any change will be done in the data will not affect the database table. Note, to make a removed entity object, we will call session.delete method. Here you can see a new instance of entities passed to transient state. Garbage is passed from transient state. Transient state is connected to persistent state. Save, persist, and save or update and update methods are passed from transient state to persistent state. Get and load methods are passed to transient state. Transient state is connected to removed state. delete method is passed from transient state to removed state, and removed state is there. Garbage is from removed state, and transient state interacts with detached state. Detach, close, clear, and evict methods are passed from transient state to detached state. Save, or update, merge, and lock methods are from detached state to persistent state. Garbage is from detached state. Here you can see converting transient state to persistent state. Here you can see using the Hibernate session, the save entity object into the database table. Here you can see using the Hibernate session, load entity object into the database table. Here transient state is connected to persistent state. Save, persist, save, update, and update methods are from transient state to persistent state. And here database is connected to persistent state. Get and load methods are from database to persistent state. Here you can see persistent objects, persistent or managed. Persistent objects are maintained by Hibernate. Persistent entities exist in the database and Hibernate's persistent context track all the changes done on the persistent entities by the client code. Persistent entity is mapped to a specific database row. Identified by the ID field. Hibernate's current running session is responsible for tracking all changes done to the managed entity and propagating these changes to a database. We can get persistent entity in either of two ways. Load the entity using get or load method. Persist the transient or detached entity using persist, save, update or save or update methods. Here client interacts with Pojo. Pojo interacts with session interacts with database. Here you can see database interacts with the Pojo table here. As an example, we can consider this code segment. Newly instantiated instances of a persistent classes are considered transient by Hibernate. We can make Hibernate instance persistent by associating it with the session. If cat has a generated identifier, the identifier is generated and assigned to the cat when save is called. If cat has an assigned identifier or composite key, the identifier should be assigned to the cat instance before calling save. You can also use persist instead of save with the semantic defined in the EGB3 early draft. Persist method makes a transient instance persistent. However, it does not guarantee that identifier value will be assigned to the persist instance immediately. The assignment might happen at flush time. Persist method also guaranteed that it will not execute an insert statement if it is called outside the transaction boundaries. This is useful in long-running conversations with an extended session persistent context. Save does guarantee to return an identifier. If an insert has to be executed to get the identifier, for example identity generator not sequence, this insert happens immediately, no matter if you are inside or outside of an transaction. This is problematic in a long-running conversation with an extended session persistence context. Here you can see a save object, persist. Here you can see a save method, persist the given transient instant, first assigning a generated identifier or using the current value of the identifier property if the assigned generator is used. This operation cascades to associated instances if the association is mapped with cascade equal save update. This method is in org.hibernate.session interface. Here you can see an example of mapping. A table lets you to define the table entity will be persisted into. If undefined, the table name is the unqualified class name of the entity. You can also optionally define the catalog, the schema, as well as unique constraints on the table. The constraints name is optional, generated if left undefined. The column names corresponding the column names composing the constraint correspond to column names as defined before the Hibernate naming strategy is applied. And you can see here column names. Here you can see an example of mapping in file hbm.xml. Now we are considering declare getters and setters for persistent attributes in entity types in domain model. The Jakarta persistence specification requires this, otherwise the model would prevent accessing the entity persistent state fields directly from outside the entity itself. Although Hibernate does not require it, it is recommended to follow the Java Bean conventions and define getters and setters for entity persistent attributes. Nevertheless, you can still tell Hibernate to directly access the entity fields. Attributes, whether fields or getters or setters, need not to be declared public. Hibernate can deal with attributes declared with the public protected package or private visibility. Again, if wanting to use runtime proxy generation for lazy loading, the getter or setter should grant access to at least package visibility. Now we are considering manage or persistent. In persistence context, the entity has an associated identifier and is associated with the persistence context. It may or may not physically exist in the database yet. Now we are considering accessing Hibernate APIs from Jakarta persistence. The Jakarta persistence defined an incredibly useful method to allow applications access to APIs of underlying provider. Now we are considering lazy attribute loading in bytecode enhancement. Here you can see at lazy group example. Annotation type lazy group specifies the fetch group for a persistent attribute of an entity class. This annotation has no effect unless bytecode enhancement is used and field level lazy fetching is enabled. This is in the package org.hibernate.annotations. Think of this as partial loading support. Essentially, you can tell Hibernate that only parts of an entity should be loaded upon fetching from the database, and when other parts should be loaded as well. Note that this is very much different from proxy based idea of lazy loading, which is entity centric, where the entity's state is loaded at once as needed. With bytecode enhancement, individual attributes or group of attributes are loaded as needed. Lazy attributes can be designated to be loaded together, and this is called a lazy group. By default, all singular attributes are part of a single group, meaning that when one lazy singular attribute is accessed, all lazy singular attributes are loaded. Lazy plural attributes by default are each lazy group themselves. This behavior is explicitly controllable through the at org.hibernate.annotation.lazy group annotation. In this example, we have two lazy attributes. We have the account payable xref id and image, each part of a different fetch group. Which means that accessing account payable xref id will not force the loading of image attribute, vice versa. As hopefully temporary legacy hold over, it is currently required that all lazy singular associations many to one and one to one also include at lazy to one lazy to one option dot no proxy. The plan is to relax that requirement later. Getters and setters are omitted for the brevity. Now we are considering making entities persistent. Here making an entity persistent with Hibernate API. The method void persist object make a transient instance persistent and mark it for later insertion in the database. This operation cascades to associated instances if the association is mapped with cascade type dot persist. This is in the interface session and in the package org.hibernate. Once we have created a new entity instance using standard new operator, it is in new state. You can make it persistent by associating it to either an org.hibernate.session or a jakarta.persistent.entity manager. Org.hibernate.session also has a method named persist, which follows the exact semantics defined in the Jakarta persistent specification for the persist method. It is this org.hibernate.session method to which the Hibernate Jakarta.persistence.entity manager implementation delegates. If the domestic cat entity type has generated an identifier, the value is associated with the instance when the save or persist is called. If the identifier is not automatically generated, the manually assigned usually natural key value has to be set on the instance before the save or persist methods are called. Now we are considering deleting, removing entities, obtaining, deleting an entity with Hibernate API. The method void remove object mark a persistent instance associated with this session for removal from the underlying database. This operation cascades to associate instances if the association is mapped cascade type dot remove. This is in the interface session and which is in the package org.hibernate. Entities can also be deleted. This is deleting an entity with Hibernate API, and this is deleting an entity with Jakarta persistence. Hibernate itself can handle deleting entities in detached state. Jakarta persistence, however, disallow this behavior. Implementation here is that entity instance passed to the Hibernate org.hibernate.session delete method can be either in managed or detached state, while entity instance passed to remove on Jakarta.persistence.entity manager must be in the managed state. Here you can see we are considering obtain an entity reference without initializing its data. Obtaining an entity reference here, obtaining an entity reference without initializing its data with Hibernate API here. The method TT get reference class T entity type object ID return a reference to the persistent instance with the given class and identifier, making the assumption that the instance is still persistent in the database. This method never results in access to the underlying data store and thus might return a proxy that is initialized on demand when non-identifier method is accessed. This is in the package, this is in the interface session, and which is in the package org.hibernate. Sometimes referred to as lazy loading, the ability to obtain a reference to an entity without having to load its data is hugely important. The most common case being the need to create an association between an entity and another existing entity. Here you can see the obtaining an entity reference without initializing its data with Jakarta persistence. Here obtaining an entity reference without initializing its data with Hibernate. These examples work on the assumption that the entity is defined to allow lazy loading, generally through use of runtime proxies. In both cases, an exception will be thrown later if a given entity does not refer to actual database state when the application attempts to use returns proxy in any way that requires access to its data. Unless the entity class is declared final, the proxy extends the entity class. If the entity class is final, the proxy will implement an interface instead. Now we are considering obtaining an entity with its data initialized. Here obtaining an entity reference with its data initialized with Hibernate API. The method get class T entity type object ID returns the persistent instance of the given entity class with a given identifier, or null if there is no such persistent instance. If the instance is already associated with the session, the return that instance. This method never returns an uninitialized instance. This is in the interface session, which is in the package org.hibernate. Obtaining an entity reference with its data initialized with Jakarta persistence. Here obtaining an entity reference with its data initialized with its data initialized using by ID method Hibernate API. In both cases, null is returned if no matching database row was found. It is possible to return in a Java 8 optional as well. Here the obtaining an optional entity entity reference with its data initialized using by ID Hibernate API. Now we are considering obtain multiple entities by their identifiers, loading multiple entities using by multiple IDs. If you want to load multiple entities by providing their identifiers, calling the entity manager dot hash find method multiple times is not only inconvenient but also inefficient. While the Jakarta persistent standard does not support retrieving multiple entities at once other than running JPQL or criteria API query, Hibernate offers this functionality via the by multiple IDs method of the Hibernate session. The by multiple IDs method returns multi-identifier load access, which you can use to customize the multi-load request. The multi-identifier load access interface provides several methods which you can use to change the behavior of the multi-load call. It's a enable order return boolean enabled, enable session check boolean enabled, enable return of deleted entities boolean enabled, with lock options, with cache mode, with batch size int batch size, with root graph t graph. Now assuming we have 3% entities in the database, we can load all of them with a single call as illustrated by this example. Here the method t multi-identifier load access, t by multiple IDs class, t entity class, create a multi-identifier load access instance to retrieve multiple entities at once as specified by the primary key values, and this is in the interface session which is in the package org.hibernate. Notice that one SQL select statement executed since the second call uses enable session check method of the multi-identifier load access to instruct Hibernate to skip entities that are already loaded in the current persistent context. If the entities are not available in the current persistent context but they could be loaded from second level cache, you can use with cache mode method of the multi-identifier load access object. In the example here, we first make sure that we clear the second level cache. In this example, we first make sure that we clear the second level cache to demonstrate that multi-load query will put the returning entities into second level cache. After executing first by multiple IDs call, Hibernate is going to fetch the requested entities and illustrated by get second level cache put count method call. 3 entities were indeed added to the shared cache. Afterward, when executing the second by multiple IDs call for the same entities in a new Hibernate session, we get the cache mode dot normal second level cache mode, so that entities are going to be returned from second level cache. The get second level cache hit count statistics method returned 3 this time, since the 3 entities were loaded from second level cache, and as illustrated by SQL statement interceptor dot get SQL queries, no multi-load select statement was executed this time. Now we are considering obtain an entity by natural ID, load entity by natural ID. Annotation type natural ID specifies that a field or property of an entity class is part of natural ID of the entity. This annotation is very useful when the primary key of an entity class is surrogated key, that is a system generated synthetic identifier with no domain model semantics. There should always be some other field or combination of fields which uniquely identifies an instance of an entity, instance of the entity from the point of view of the user of the system. This is the natural ID of the entity. This is in the package org.hibernate.annotations. In addition to allowing to load the entity by its identifier, Hibernate allows application to load entities by the declared natural identifier. This is a natural ID mapping here. You can also opt to fetch an entity or just retrieve a reference to it when using natural identifier loading methods. Here get entry reference by simple natural ID, load entity by natural ID, we can also use Java 8 optional to load entity by its natural ID. Hibernate offers a consistent API for accessing persistent data by identifier or by natural ID. Each of these define the same two data access methods. Get reference should be used in cases where the identifier is assumed to exist, where non-existence would be an actual error. There should never be used to test existence. That is because this method will prefer to create and return a proxy of if the data is not already associated with the session rather than hit the database. The quintessential use case for using this method is to create foreign key based on associations. Load will return the persistent data associated with the given identifier value or null if that identifier does not exist. Each of these methods defines an overloading variant accepting org.hibernate.lock options argument. Locking is local lock options argument. Getters and setters are omitted for brevity. Now we are considering at-where in filtering entities and associations. Here at-where mapping usage. Sometimes you want to filter out entities or collections using custom SQL criteria. This can be achieved using where annotation which can be applied to entities and collections. Annotation type where specifies a restriction written in native SQL to add to generated SQL when querying an entity collection. If the database contains the following entities, here the persistent and fetching entities with where mapping, getters and setters omitted for brevity. Getters and setters omitted for brevity. Um, when executing an account entity query, Hibernate is going to filter out all the records that are not active. Now we are considering modifying managed and persistent or persistent state. Here modifying managed state with the Hibernate API. Entities, here the method void flush force this session to flush must be called at end of a unit of work before transaction is committed. Depending on the current flush mode, the session might automatically flush when entity transaction.commit method is called, and it is not necessary to call this method directly. This is in the interface session and in the package org.hibernate. Entities in managed persistent state may be manipulated by the application, and any changes will be automatically detected and persisted when persistence context is flushed, where there is no need to call a particular method to make your modification persistent. Here modifying managed state with Jakarta persistence. Here modifying managed state with Hibernate API. By default, when you modify an entity, all columns but the identifier are being set during update. Now we are considering refresh entity state. Refreshing entity state with Hibernate, here Hibernate API. Method void refresh object reread the state of the given managed instance associated with this session from the underlying database. This may be useful when a database trigger alters the object state upon insert and update, after executing any HQL update or delete statement, after executing a native SQL statement, after inserting a blob or club. This is in the interface session and it is in the package org.hibernate. You can load an entity instance and its collections at any time. Refreshing entity state with Jakarta persistence here. Refreshing entity state with Hibernate API is here. One case where it is useful when it is known that the database state has changed since the data was read. Refreshing allows the current database state to be pulled into the entity instance and the persistence context. Another case where this might be useful is when database triggers are used to initialize some of the properties of the entity. Only the entity instance and its value type collections are refreshed unless you specify refresh as a cascade style of any associations. However, please note that Hibernate has the capability to handle this automatically through its notion of generated properties. Traditionally, Hibernate allowed at detached entities to be refreshed. Unfortunately, Jakarta persistence prohibit this practice and specifies that illegal argument exception should be thrown instant. For this reason, when bootstrapping the Hibernate SessionFactory using the native API, the legacy detached entity refresh behavior is going to be preserved. On the other hand, when bootstrapping the Hibernate through Jakarta persistence, entity manager factory building process detached entities are not allowed to be refreshed by default. However, this default behavior can be overridden through Hibernate.allow refresh detached entity configuration property. If this property is explicitly set to true, then you can refresh detached entities even when using Jakarta persistence bootstraps mechanism, therefore bypassing the Jakarta persistence specification restriction. Now we are considering working with considering reattaching detached data in working with detached data. Here reattaching a detached entity using lock. The method void lock object lock options obtaining a lock on the given manage instance associated with this session using the given lock options. This is in the interface session and it is in the package org.hibernate. Reattachment is the process of taking incoming entity instance that is in the detached state and associating with it with the current persistence context. Jakarta persistence does not support reattaching detached data. This is only available through Hibernate org.hibernate.session. Here reattaching detached entity using lock. Here reattaching detached entity using save or update. The method name update is a bit misleading here. It does not mean that SQL update is immediately performed. It does however mean that SQL update will be performed when the persistent context is flushed, since Hibernate does not know previous state against which to compare for changes. If the entity is mapped with select before update, Hibernate will pull the current state from the database and see if update is needed. The provided entity is detach update and save update operate exactly the same. Here it's not shown here, but you can see the merge is there. Clear session on the person entity becomes detached. Clear session on the person entity becomes detached. Now we are considering checking persistence state and verify manage state with Hibernate API here. An application can verify the state of entities and collections in relation to the persistent context. Here verify manage state with Jakarta. Verify manage state with Jakarta persistence. Here verify manage state with Hibernate API. Here now we are considering evicting entities. Here you can see evicting an entity from the Hibernate session. Here the method void evict object remove this instance from the session cache. Changes to the instance will not be synchronized with the database. This operation cascades to associated instances if the association is mapped with cascade type detached. This is in the interface session and which is in the package org.hibernate. When the flush method is called, the state of the entity is synchronized with the database. If you do not want this synchronization to occur, or if you are processing a huge number of objects and need to manage memory efficiently, the evict method can be used to remove the object and its collections from the first level cache. Here you can see the detach entity from entity manager. Here you can see evicting an entity from Hibernate session. To detach all entities from the current persistence context, both the entity manager and the Hibernate session defines a clear method. Here clearing the persistence context. To verify if an entity instance is currently attached to the running persistence context, the both entity manager and the Hibernate session define contains object entity method. Here verifying if an entity is contained in a persistent context. Now we are considering cascading entity state transitions. The following example will explain some of the aforementioned cascade operations using the following entities. Public static final cascade type all includes all types listed here and equivalent to cascade type all. This is in the enum cascade type, which is in the package org.hibernate.annotations. Jakarta persistence allows you to propagate the state transition from a parent entity to child. For this purpose, Jakarta persistence or cascade type define various cascade types. All means cascade all entry state transitions, and persist merge, persist cascade entity persistence operation, merge, remove, refresh, detach. Additionally, the cascade type all will propagate any Hibernate specific operations, which is defined by the org.hibernate.annotation.cascade type enum. They are save underscore update, replicate, lock. The following example will explain some of the aforementioned cascade operations using following entities here. Here as an example, cascade type dot persist. The cascade type dot persist allows us to persist the child entity along with parent one. So here the cascade type persist example here. Even if just parent entity was persisted, Hibernate has managed to cascade the persistent operation to the associated phone child entity as well. Now we are considering exception handling. Here constraint violation exception indicates some form of integrity constraint violation. This is the class constraint violation exception. A JDBC exception indicating that the request's DML operation resulted in violation of defining integrity constraints. This is in the package of Hibernate.exception. As an example, we can consider class persistent object exception thrown when the user passes a persistent instance to a session method that expects a transient instant. This class is in org.hibernate package. As an error example, we can consider this detach entity pass to the persist com.bwt.spindle.model.plot. Now we are focusing on session, the main runtime interface between Java application and Hibernate. This is the central API class abstracting the notion of a persistence service. The lifecycle of a session is bounded by the beginning and end of a logical transaction. Long transactions might span several database transactions. The main function of the session is to offer create, read, and delete operations for instances of mapped entity classes. Instances may exist in one of three states: transient, never persistent, not associated with any session; persistent, associated with a unique session; detached, previously persistent and not associated with any session. Transient instances may be made persistent by calling save persist and or save or update. Persistent instances may be made transient by calling delete. Any instance returned by a get or load method is persistent. Detached instances may be made persistent by calling update, save or update, locked, or replicate. The state of a transient or detached instance may also be made persistent as a new persistent instance by calling merge save and persist methods result in an SQL insert, delete method in SQL delete, and update method or merge method in an SQL update. Changes to persistent instances are detached at flush time and also result in an SQL update. Save or update method and replicate method result in either an insert or an update. It is not intended that implementers be thread safe. Instead, each thread transaction should obtain its own instance from a SessionFactory. A session instance is serializable if its persistent classes are serializable. If the session throws an exception, the transaction must be rolled back and the session discarded. The internal state of the session might not be consistent with the database after the exception occurs. Here you can see session methods that make state transitions happen. An entity instance in our application appears in one of three main states in relation to the session persistence context. Transient. This transient isn't and never was attached to a session. This instance has no corresponding rows in the database. It's usually just a new object that we created to save to the database. Persistent. This instance is associated with a unique session object. Upon flushing the session to the database, this entity is guaranteed to have corresponding consistent record in the database. Detached. This instance was once attached to a session. In a persistent state, but now it's not. An instance entered this state if we evict it from context, clear or close the session, or put the instance through serialization, deserialization process. When the entity instance is in the persistent state, all the changes that we make to the mapped fields of this instance will be applied to the corresponding database records and fields upon flushing session. The persistent instance is online, whereas the detached instance is offline and not monitored for changes. This means that when we change the fields of a persistent object, we don't have to call save, update or any of those methods to get these changes to the database. All we need to do is commit the transaction, flush the transaction or close the session. Persist. The persist method is intended to add a new entity instant to the persistent context. That is transitioning an instance from transient to persistent state. Save. The save method is an original Hibernate method that doesn't conform to the JPA specification. Its purpose is basically the same as persist, but it has different implementation details. The documentation for this method strictly states that it persists the instant, first assigning a generated identifier the method will return serializable value of this identifier. Merge. The main intention of the merge method is to update a persistent entity instance with new field values from the detached entity instance. For instance, suppose we have RESTful interface with the method of retrieving a JSON serialized object by its ID to the caller, and the method that receives an update version of this object from the caller. An entity that passed through such serialization deserialization will appear in a detached state. After deserializing this entity instance, we need to get a persistent entity instance from a persistent context and update its field with new values from this detached instance. So the merge method does exactly that. Find an entity instance by ID taken from past object. Either an existing entity instance from the persistent context is retrieved, or a new instance loaded from database. Copies fields from the past object to the instance, returns a newly updated instance. Update. As with persist and save, it's the update method is an original Hibernate method. Its semantics differ in several key points. It acts upon a past object. Its return type is void. The update method transitions the past object from detached to persistent state. This method throws an exception if the pass is in if we pass it a transient entity. Save or update. This method appears only in Hibernate API and doesn't have its standardized counterpart similar to update. We can also use it for reattaching instances. Actually, the internal default update event listener class that processes the update method is a class of default save or update listener, just overriding some functionality. The main difference of the save or update method is that it doesn't throw an exception when we applied to a transition instance. Instead, it makes it transient instance persistent. Here you can see a new is passed to transient, and transient interacts with persistent. Save persistent. Save persist. Save updates are from transient to persistent. Delete is from persistent to transient. Persistent object is inside in the session. Persistent interacts with detach, evict, and session.close are passed from persistent to detach. Locked, update, merge, and save or update are passed from detach to persistent. Get, load, and SQL query to persistent. We can consider this code segment as an example. SessionFactory in Hibernate 5 example here, and local SessionFactory bin is created here, and here you can see interface session. The main runtime interface between a Java application and Hibernate. This is the central API class abstracting the notion of a persistent service, and this is in org.hibernate package. Here we can consider this segment in hibernate.cfg.xml file. Here you can see set the current session context here, and you can see the property hibernate.current session context class here. Supply a custom strategy for scoping of the current session. Example JTA thread managed custom.class. Now we are considering interface session. The main runtime interface between a Java application and Hibernate represents the notion of a persistent context, a set of managed entity instances associated with the logical transaction. This is in the package org.hibernate. Now we are considering session.lock method in locking. This is a session.lock example. The void lock object and lock options obtain a lock on a given managed instance associated with this session using the given lock options. This is in the interface session, and which is in the package org.hibernate. The following example shows how to obtain a shared database locked. Now we are considering session batching. In batching, here is a naive way to insert 100,000 entities with Hibernate. The following example shows an anti-pattern for batch inserts. There are several problems associated with this example. 1. Hibernate caches all newly created custom instances in the session level cache. So when the transaction ends, 100,000 entities are managed by the persistent context. If the maximum memory is allocated to the JVM is rather low, in this example could fail with an out of memory exception. The Java 1.8 JVM allocated either quarter of the available RAM or 1 GB, which can easily accommodate 100,000 objects in the heap. 2. Long-running transactions can deplete a connection pool, so rather transaction don't get a chance to proceed. 3. JDBC batching is not enabled by default, so every insert statement requires a database round trip. To enable JDBC batching, set the hibernate.jdbc.batch_size property to an integer between 10 and 50. Hibernate disables insert batching at the JDBC level transparently if you use the identity identifier generator. Now we are considering batch insert, flushing and clearing session, clearing the session. The method void flush force this session to flush must be called at the end of the unit of work before the transaction is committed. Depending on the current flush mode, the session might automatically flush when entity transaction.commit is called, and it is not necessary to call this method directly. Void clear method completely clear the session, evict all loaded instances and cancel all pending saves, updates and deletions. Do not close open iterators or instances of scrollable results. We are discussing about the flush method and clear methods in interface session, which is in the package org.hibernate. When you make new object persistent, employ method flush, methods flush and clear to the session regularly to control the size of the first level cache. Here you can see flushing and clearing session. Flush the batch of inserts and release memory. Now we are considering session scroll using scroll method. The method scrollable result are scroll mod returns scrollable access to the query results. The capabilities of return scrollable results depending on the specified scroll mode. This is in the interface selection query R, which is in the package org.hibernate.query. When you retrieve and update data, flush and clear the session regularly. In addition, use method scroll to take advantage of server-side cursors for queries, and that returns many rows of data. If left unclosed by the application, the Hibernate will automatically close the underlying resources, for example, result set and prepared statement used internally by scrollable result. When the transaction is ended, either commit or rollback. However, it is good practice to close scrollable results explicitly. Flush the batch, updates and release the memory. Here now we are considering stateless session. Using a stateless session interface stateless session, a command-oriented API often used for performing bulk operations against the database. A stateless session has no persistent context and always works directly with detached entity instance. Thus, when a method of interface is called, by necessarily interaction with the database happens immediately and synchronously. This is in the package Hibernate org.hibernate. The stateless session is an alternative session and provides a command-oriented API with no associated persistence context. Thus, a stateless session is slightly lower level abstraction that is closer to the underlying JDBC activity. There is no first level cache. The stateless session does not interact with any second level or query cache. There is no transactional write behind or automatic dirty checking. Instead, persistent operations occur synchronously when a method of stateless session is invoked. The entities returned by the stateless sessions are always detached. A stateless session may be used to stream data to and from the database in the form of detached object. With the stateless session, there is no need to explicitly manage the size of the first level cache by explicitly clearing the persistent context. The stateless session API comes with certain limitations. Operations performed using a stateless session never cascade to associated instances. Collections are ignored by a stateless session. Lazy loading of associations is not transparent and only available via an explicit operation named fetch. And operations performed via a stateless session bypass Hibernate's event model and interceptors. Due to the lack of first level cache, stateless sessions are vulnerable to data aliasing effects. Here using stateless session, the customer instances returned by the query are immediately detached. They are never associated with any persistence context. The insert method, update method, and delete operations defined by the stateless session interface operate directly on database rows. They cause corresponding SQL operations to be executed immediately. They have different semantics from the save, update, and delete operations defined by session interface. Here the interface stateless session, a command-oriented API often used for performing bulk operation against the database. A stateless session has no persistence context and always work directly with detached entity instances. When a method of this interface is called, any necessary interaction with the database happens immediately and synchronously. This is in the package org.hibernate. Now we are considering multi-tenancy Hibernate session configuration in multi-tenancy in Hibernate in multi-tenancy. The Hibernate session can be configured using the tenant-specific context. When using multi-tenancy, you might want to configure each tenant-specific session differently. For instance, each tenant could specify different time zone configuration. The register connection provider method is used here to define the tenant-specific context. For our example, the tenant-specific context is held in the connection provider map and time zone tenant map. Now when building a Hibernate session, aside from passing the tenant identifier, we could also configure the session to use the tenant-specific time zone. Here the Hibernate session can be configured using tenant-specific context. So if we set the time use tenant time zone parameter to true, Hibernate will persist the timestamp properties using tenant specific time zone. As you can see in the following example, timestamp is successfully retrieved even if the current running JVM uses a different time zone. Here the tenant use tenant specific time zone. Here use tenant time zone allows you to persist a timestamp with the provided time zone. However, behind the scenes, we can see that Hibernate has saved the create_on property in the tenant specific time zone. Now we are considering session statistic methods in org.hibernate.stat.statistics method in statistics. Get session close count, global number of sessions that got closed. The method long get session close count, the global number of sessions closed. This is in the interface statistics, and which is in the package org.hibernate.stat. Now we are considering hibernate.session.events.auto in session events, fully qualified class name implementing the session event listener interface. As an example, we can consider, as an exception example, we can consider session exception class thrown when the user calls a method of a session that is in an inappropriate state for the given call. For example, the session is closed or disconnected. This class is in org.hibernate package. As an example, we can consider this: no current session context configured, org.hibernate.implement.SessionFactory implement.get current session. Now we are focusing on SessionFactory. The main contract here is the creation of session instances. Usually an application has a single SessionFactory instance, and threads servicing client requests obtain sessions instances from this factory. The internal state of a SessionFactory is immutable. Once it is created, this internal state is set. This internal state includes all of the metadata about object relational mapping. Implementers must be thread safe. Here you can see SessionFactory and session in Hibernate. SessionFactory is an interface available in org.hibernate package, which extends referenceable and serializable interface and provide factory methods to get session object. Let's see some points about this SessionFactory. SessionFactory is thread safe, so multiple threads can access SessionFactory at the same time. SessionFactory is immutable. Once we create SessionFactory, we can not modify it. If you look SessionFactory methods, we don't have any setter kind of method. SessionFactory is created at the time of application startup. It reads all information from the configurable file. Hibernate.cfg.xml file. We should have one SessionFactory for one database configuration. We can create SessionFactory object using configuration class. Here first we are creating configuration class object and call configure method. Which has two overloaded versions, one without parameter like configure method, and another one is configure string resources. If we use configure without parameters method, hibernate.cfg.xml is defined. Session is an interface available in org.hibernate package, which provide different API to communicate Java application to Hibernate. Let's see some points related to session. The session is not thread safe. The main use of the session object to perform create, get, and delete operations for Java classes entity. The first level cache belongs to the session object. We can have multiple sessions for a session factory. We can get session object using SessionFactory reference. As here. Here you can see configuration. You can see the code here. Configuration config equal new configuration dot configure, and configuration is connected to SessionFactory. You can see config.build SessionFactory method here to get a SessionFactory object, and SessionFactory is connected to session. You can see factory dot open session method to get a session here. As an example, we can consider this code segment, and here you can see the interface SessionFactory. The main contract here is the creation of session interfaces. Usually an application has a single SessionFactory instance, and thread serving client request obtain session instances from this factory. This interface is in org.hibernate package. Here you can see build SessionFactory method is called. Here you can see the XML configuration file is by default expected to be in the root of your class path. Here's an example here. The file is hibernate.config.xml here, and here you can see a SessionFactory instance listed as /JNDI /name, SessionFactory name, this one. We can see properties here and mapped files here and cache settings here. Now we are considering SessionFactory. Interface SessionFactory. A SessionFactory represents an instance of Hibernate. It maintains the runtime meta model representing persistent entities, their attributes, their associations, and their mappings to the relational tables, along with configuration that affects the runtime behavior of Hibernate and instances of services that Hibernate needs to perform its duties. This is in the package org.hibernate. Now we are considering native Hibernate APIs and HBM.xml mapping. In his example code, obtaining the org.hibernate SessionFactory. The method SessionFactory built SessionFactory. Shorthand form of building a SessionFactory through the builder without any additional option overrides. This is in the interface metadata, which is in the package org.hibernate.boot. The org.hibernate.tutorials.hbm.native API illustration test class illustrates using the Hibernate native API. The examples in this here are presented as JUnit test for ease of use. One benefit of this approach is set up and tear down regularly, roughly illustrate how org.hibernate.SessionFactory is created at the startup of an application and close at the end of the application life cycle. Here the example obtaining the org.hibernate.SessionFactory. The setup methods first built org.hibernate.boot.registry.standard service registry instance, which incorporate configuration configuration information into working set of services for use by SessionFactory. In this here we define all configuration information in hibernate.cfg.xml, so there is not much interesting to see here. Using a standard service registry, we create org.hibernate boot.meta data sources, which is the starting point for telling Hibernate about your domain model. Again, since we define that in hibernate.cfg.xml, so there is not much interesting to see here. org.hibernate.boot.metadata represent the complete partially validated view of the application domain model, which the SessionFactory will be based on. The final step in the bootstrap process is to build the SessionFactory. The SessionFactory is a thread-safe object that is instantiated once to serve the entire application. The SessionFactory acts as a factory for org.hibernate.session instances, which should be thought of as a corollary to a unit of work. A SessionFactory is set up once for an application. Configure settings from the hibernate.cfg.xml. Registry would be destroyed by the SessionFactory, but we had the trouble building the SessionFactory so destroy it manually. Now we are considering building the SessionFactory in native bootstrapping in Bootstrap. Here the native bootstrapping, putting it all together here. The interface session factory builder, the contract for building a session factory given a number of options. This is the package org.hibernate.boot. The final step in native bootstrapping is to build the session factory itself, much like we discussed before. If you are okay with the default behavior of building session factory from metadata reference, you can simply call build session factory method on metadata object. However, if you would like to adjust the building process, you will need to use the session factory builder as obtained via metadata dot get session factory builder. Here we are considering building session factory via session factory builder. The interface session factory builder, the contract for building session factory given a number of options. This is in the package org.hibernate.boot. The bootstrapping API is quite flexible, but in most cases it makes the most sense to think of it as three-step process. 1, build the standard service registry. 2, build the metadata. 3, use those two to build session factory. Supply a session factory level interceptor. Add a custom observer. Apply CDI bean manager for JPA event listeners. Now we are considering configuring the session factory metadata via the Jakarta persistence bootstrap. In Jakarta persistence bootstrapping in bootstrap. Here implementing meta builder contributor. Interface meta builder contributor, a bootstrap process hook for contributing settings for meta builder. This is in the package org.hibernate.boot.spi. As previously seen, the Hibernate native bootstrap mechanism allows you to customize a great variety of configuration which are passed via metadata object. When using Hibernate as a Jakarta persistent provider, the entity managed factory is backed up by SessionFactory. For this reason, you might still want to use metadata object to pass various settings which cannot be supplied via the standard Hibernate configuration settings. For this reason, you can use metadata builder contributor class, as you can see in this example. Here, implementing a metadata builder contributor. org.hibernate.orm.test.bootstrap.spi.metadata builder contributor. The above metadata builder contributor is used the above metadata builder contributor is used to register SQL function which is not defined by the currently running Hibernate dialect, but which we need to reference in our JPQL queries. By having access to the metadata builder, class that is used by the underlying SessionFactory, the Jakarta persistent bootstrap becomes just as flexible as Hibernate native bootstrap mechanism. You can then pass the custom metadata builder contributor via the Hibernate.metadata_builder_contributor configuration property. Now we are considering SessionFactory statistics method in org.hibernate.stat.statistics methods in statistics. Get entity names. Get the names of all entities configured with the current SessionFactory. The method string array get entity names of all entities. This is in interface statistics, which is in the package org.hibernate.stat. Now we are considering SessionFactory service registry in SessionFactory service in types of service registries in services and registries. org.hibernate.service.spi.SessionFactory service registry is the third standard Hibernate service registry. Interface SessionFactory service registry, specialized service registry implementation that holds services which needs to access the SessionFactory during initialization. This is in the package org.hibernate.service.spi. SessionFactory service registry is designed to hold services which need to access the SessionFactory. Typically, its parent registry is standard service registry. Integrators, as it stands in 4.x, operate on the SessionFactory service registry. Currently, SessionFactory service registry holds 4 services: event listener registry, statistics implementer, native query interpreter, and cache implementer. An example we can consider as an exception example, we can consider Hibernate exception. This indicates a problem opening the session, pretty rare here. for example, this exception can occur in open session method in interface SessionFactory. As an error example, we can consider this one. The content of element type SessionFactory must match property mapping class cache collection cache event listener. Now we are focusing on TransactionFactory. Contract for generating Hibernate this is in hibernate.cfg.xml file, and here you can see Hibernate transaction property transaction.factory underscore class. The class name of a transaction factory to use with Hibernate transaction API, default to JDBC transaction factory. For example, class name dot of transaction factory. Now we are considering interface transaction factory. Contract for generating Hibernate transaction into instances. This is in the package org.hibernate.transaction. In older version Hibernate 3.5. As an exception example, we can consider Hibernate exception. Indicates a problem generating a transaction instance. This exception can be occurred in method transaction create transaction JDBC context TransactionFactory.context method in interface transaction factory. Now we are focusing on ConnectionProvider, a strategy for obtaining JDBC connections. Implementers might also implement connection pooling. The ConnectionProvider interface is not intended to be exposed to the application. Instead, it is used internally by Hibernate to obtain connections. Implementers should provide a public default constructor. Hibernate will internally determine which connection provider to use based on the following algorithm. One, if hibernate.connection.provider underscore class is set, it takes precedence. Two, else if hibernate.connection.dataSource is set using data sources. Three, else if any settings prefixed by Hibernate.c3p0 is set using c3p0. For else if any setting prefixed by Hibernate.proxol is set using proxol. 5. Else if any setting prefixed by Hibernate.hikari is set using hikari cp. 6. Else if any settings prefixed by Hibernate.vibo is set using vibo dbcp. 7. Else if any settings prefixed by Hibernate.agrol is set using agrol. 8. Else if Hibernate.connection.url is set using Hibernate's built-in and unsupported pooling. 9. Else user provided connections. As an example, we can consider this code segment. Interface connection provider, a strategy for obtaining JDBC connections. This is in package org.hibernate.connection. As an example 2, we can consider this segment in hibernate.cfg.xml file. Here you can see Hibernate, JDBC and connection property hibernate.connection.provider underscore class. The class name of a custom org.hibernate.connection.connection provider, which provide JDBC connection to the Hibernate. For example, class name of connection provider. Here 3C here C3PO, a Java library that provides a convenient way for managing database connections. Now we are considering interface connection provider. A contract for obtaining JDBC connections and optionally for pooling connections. This is in the package org.hibernate.engine.jdbc.connection.connections.spi. Now we are considering connection provider in database access. Same as the previous example, here we are considering org.hibernate.engine.jdbc.connections.spi.connection provider. This is the ultimately in the function of the org.hibernate.engine.jdbc.connections.spi.connection provider interface. The interface connection provider, a contract for obtaining JDBC connections and optionally for pooling connections. This is in the package org.hibernate.engine.jdbc.connections.spi. As an ORM tool, probably the single most important thing you need to tell Hibernate is how to connect to your database so that it may connect on behalf of your application. This is ultimately the function of the org.hibernate.engine.jdbc.connections.spi.connection provider interface. Hibernate provides some out-of-box implementation of this interface. Connection provider is also an extension point, so you can use custom implementation for third parties or even yourself. The connection provider to use is defined by the hibernate.connection.provider underscore class string. Generally speaking, applications should not have to configure a connection provider explicitly if using one of the Hibernate provided implementations. Hibernate will internally determine which connection provider to use based on the following algorithm. 1. If Hibernate.connection.provider underscore class is set, it takes precedence. 2. Else if hibernate.connection.data source is set using data sources. 3. Else if any setting prefixed by hibernate.c3p0 is set using c3po. 4. Else if any setting prefixed by hibernate.proxol is set using proxol. 5. Else if any setting prefixed by hibernate.hikari is set using hikari cp. 6. Else if any settings prefixed by hibernate.viber is set using viber dbcp. 7. Else if any setting prefixed by hibernate.egorol is set using egorol. Else if hibernate.connection.url is set using hibernate built-in and unsupported pooling. 9. Else user provided connections. Now we are considering connection provider support for transaction isolation setting. All of the provided connection provider implementations other than data source connection provider support consistent setting of transaction isolation for all connections obtained from the underlying pool. Now we are considering multi-tenant connection provider in multi-tenancy in Hibernate in multi-tenancy. Here a multi-tenant connection provider implementation. Interface multi-tenant connection provider. A specialized connection provider contract used when the application is using multi-tenancy support requiring tenant-aware connections. A class abstract multi-tenant connection provider, basic support for multi-tenant provider implementations using individual connection provider instances per tenant behind the scene. When using either the separate database or separate schema approach, Hibernate needs to be able to obtain connections in the tenant specific manner. This is the role of multi-tenant connection provider contract. Application developers will need to provide an implementation of this contract. Most of its methods are extremely self-explanatory. The only ones which might not be are get any connection and release any connection. It is important to note that also that these methods do not accept the tenant identifier. Hibernate uses this method during startup to perform various configuration, mainly via the java.sql.database metadata object. The multi-tenancy connection provider to use can be specified in a number of ways. Use the hibernate.multi-tenant connection provider setting. It could name the multi-tenant connection provider instance, a multi-tenant connection provider implementation class reference, or a multi-tenant connection provider implementation class name. Pass directly to org.hibernate.boot.registry.standard service registry builder. If none of the above options match, but the settings do specify hibernate.connection.data source value, Hibernate will assume it should use the specific data source based multi-tenant connection provider IMPL implementation, which works on a number of pretty reasonable assumptions when running inside an app server or using javax.sql.data source per tenant. The following example portrays a multi-tenant connection provider implementation that handles multiple connection providers. This is multi-tenant connection provider implementation here. The configurable multi-tenant connection provider can be set up as follows here. This is a multi-tenant connection provider usage example. When using multi-tenancy, it is possible to save an entity with the same identifier across different tenants. An example of saving entities with the same identifier across different tenants are here. Now we are considering custom services. Custom services in services and registries in Hibernate ORM 6.2 integration guide. Here custom connection provider implementation. Here custom service implementation overriding here. You can see here custom connection provider implementation. Let's look at an example in practice here. For the sake of illustration, let's say that we have developed a new connection provider integrating with the wonderful new latest and great connection pooling library. Let's look at the steps necessary to make that happen. First step is to develop actual integration by implementing connection provider contract. At this point, we have a decision about how to integrate this new connection provider into Hibernate. As you might guess, there are multiple ways. As a first option, we might just require that code bootstrapping the standard service registry to do the integration. Here overriding service implementation via standard service registry builder. Second option is if our latest and greatest connection provider IMPL should always be used, would be to provide org.hibernate service contributor implementation as well to handle the integration on the user's behalf. We still need to be able to tell Hibernate to perform integration for us. To do that, we leverage a Java's service loader when building standard service registry. Hibernate will look for JDK service providers of type org.hibernate.service.spi.service-contributor and automatically integrate them. We discussed this behavior before, and here we have done a class path resource name meta dash inf/services/org.hibernate.service.spi.service-contributor. This file will have just a single line naming our implementation, our IMPL. The meta-inf/services.org.hibernate.services.spi.service-contributor fully.qualify.package.latest and greatest connection provider IMPL contributor 1. Third option is a third option. If we simply want to make our latest greatest connection provider IMPL available as a configuration choice, we would gain a service contributor but slightly different way. This is latest and greatest connection provider IMPL contributor variation. That all allows the application to pick our latest and greatest connection provider IMPL by a short name. Extract our config from the settings map. Start the underline period. Start the underline pool. Stop the underline pool. Here we will register a short name for our service strategy. As an exception example, we can consider SQL exception, which can be occurred in connection get connection method in interface connection provider. As an error example, we can consider this one, java.lang.no class definition found error org / hibernate / connection / ConnectionProvider. This occurred in Hibernate 4. Now we are focusing on transaction. Allows the application to define units of work while maintaining abstraction from the underlying transaction implementation. For example, JTA, JDBC. A transaction is associated with a session and it is usually instantiated by a call to a session.begin transaction method. A single transaction, a single session might span multiple transactions, since the notion of a session, a conversion between the application and the data store, is of course granularity than the notion of a transaction. However, it is intended that there be at most one uncommitted transaction associated with a particular session at any time. Implementers are not intended to be thread safe. Here you can see Hibernate transaction management example. A transaction simply represent a unit of work. In such case, if one step fails, the whole transaction fails, which is termed as atomicity. Transaction can be described by acid properties: atomicity, consistency, isolation, and durability. In Hibernate framework, we have transaction interface that defines the unit of work. It maintains abstraction from the transaction implementation, JTA, JDBC. The methods of transaction interface are follows. Void begin starts a new transaction. Void commit ends a unit of work unless we are in flush mode .never. Void rollback forces this transaction to roll back. Void set timeout int seconds. It sets the transaction timeout for any transaction started by subsequent call to begin on this instance. Boolean is alive checks if the transaction is still alive. Void registers synchronization registers a user synchronization callback for this transaction. Boolean was committed, check if the transaction is committed successfully. Boolean was rollback, check if the transaction is rolled back successfully. Here you can see transaction persistence context. The transaction persistence context is bound to the transaction. As soon as the transaction finishes, the entities present in the persistent context will be flushed into the persistent storage. When we perform any operation inside the transaction, the entity manager checks for a persistent context. If one exists, then it will be used, otherwise it will create a persistence context. The default persistence context type is type is persistence context type .transaction. To tell the entity manager to use the transaction persistence context, we simply annotate it with @persistence context. Here you can see Entity Manager 1, Entity Manager 2, Entity Manager 3 are inside application. Entity Manager 1 interact with persistence context via operation. Entity Manager 2 interacts with persistent context via operation. Entity Manager 3 interacts with persistent context via operation. User 1 is inside the persistent context here. Persistent context is interacts with persistent context interacts with DB. Persistent context is connected to DB via persist. DB is connected to persistent context via find. Now we are considering extended scope persistent context. Here you can see extended persistent context. As extended persistent context can span across multiple transactions, we can persist the entity without the transaction but cannot flush it without the transaction. To tell Entity Manager to use extended scope persistent context, we need to apply the type attribute of persistent context, like here. In the stateless session bin, the extended persistence context in one component is completely unaware of any persistent context of another component. This is true even if both are in the same transaction. Let's say we persist some entity in a method of a component A which is running in a transaction. We then call some of the method in component B. The component B's method persistent context will not we will not find the entity we persist previously in the method component A. Here you can see Entity Manager 1, Entity Manager 2, Entity Manager 3 are inside application. Entity Manager 1 interacts with persistent context via operation. Entity Manager 2 interacts with persistent context via operation. Entity Manager 3 interacts with persistent context via operation. User 1 here, user 1 and user 1 and user 1 are in persistent context. Persistent context interacts with DB. Persistent context is connected to DB via persist. DB is connected to persistent context via find. As an example, we can consider this code here. Here you can see start transaction, here starts transaction, session.begin transaction here. Save the student object here and commit transaction here, transaction.commit, and rollback transaction if there's exception occurred. And interface transaction allows the application to define units of work while maintaining abstraction from the underlying transaction implementation. For example, JTA, JDBC. This is in package org.hibernate. As an example too, we can consider jta.user transaction in hibernate.csg.xml. Hibernate transaction property jta.user transaction. A JNDI name used by JTA TransactionFactory to obtain the JTA user transaction from the application server. For example, JNDI /composite/name. Now we are considering interface transaction. Represent a resource local transaction where resource local is interpreted by Hibernate to mean any transaction under the control of Hibernate. That is to say, the underlying transaction might be a JTA transaction or it might be a JDBC transaction, depending on how Hibernate is configured. This is in the package org.hibernate. Now we are considering using example code in using native Hibernate APIs and HBM.xml mapping. Here saving entities. SessionFactory acts as a factory for org.hibernate .session instances, which should be thought of as a corollary to a unit of work. Here the test basic usage method first create some new event objects and hand them over to Hibernate for management using save method. Hibernate now takes the responsibility to perform an insert on the database for each event. Here obtaining a list of entities. Here we see an example of Hibernate query language HQL to load all existing events, objects from database by generating appropriate SQL select appropriate select SQL, sending it to the database and populating event object with the result set of data. Here you can see begin transaction. Here you can see a get transaction.commit. Here you can, we are considering using the Java persistent API Jakarta persistence. Here you can see example code, and here we are saving persisting entities. Here we are using Jakarta persistent API. Here the obtaining the Jakarta.persistent.entity manager factory. Notice again that the persistence unit name is org.hibernate.tutorial.jpa, which matches persistent.xml here. Here saving persisting entities. The code similar to saving entities. The Jakarta.persistent.entity manager interface is used instead of org.hibernate.session interface. The Jakarta persistence call this operation persist instead of save. Here obtaining a list of entities. Again, the code is pretty similar to what we saw in obtaining list of entities. Now we are considering ConnectionProvider support for transaction isolation setting in database access. The value for Hibernate.connection.isolation can be specified in one of three formats. The property Hibernate.connection.isolation JDBC transaction isolation level only when using java.sql.driver manager. Here the value for Hibernate.connection.isolation can be specified in one of three formats. The integer value accepted at the JDBC level, the name of the java.sql.connection, a constant field representing isolation you would like to use. For example, transaction underscore repeatable underscore read for java.sql.connection hash connection underscore repeatable underscore read. Note that this is only supported for JDBC standard isolation levels, not for isolation level specific to a particular JDBC driver. A short name version of the java.sql.connection constant field without the transaction underscore prefix. For example, repeatable underscore read for java.sql.connection hash connection transaction underscore repeatable underscore read. Again, this is only supported for JDBC standard isolation levels, not for isolation level specific to a particular JDBC driver. Now we are considering resource underscore local transaction connection handling in transaction type and connection handling in connection handling. For resource underscore local transaction, the connection handling mode is delayed underscore acquisition underscore and underscore release underscore after underscore transaction, meaning that the database connection is acquired when needed and released after the current running transaction is either committed to rollback. The enum constant, the public static final persistent unit transaction type resource local, enum persistent unit transaction type, this is in the enum persistent unit transaction type, the persistent enum persistent unit transaction type Java class for persistent unit transaction type package. This is in the package design the package org.hibernate.jpa model gen.xml.jaxb. However, because Hibernate needs to make sure that the default auto commit mode is disabled, the JDBC connection when starting new transaction, the connection is acquired and the auto commit mode is set to false. If you are using connection pool data source that already disabled the auto commit mode for every pooled connection, you should set the Hibernate.connection.provider underscore disables underscore auto commit to true, and the database acquisition will be indeed delayed until Hibernate needs to execute the first SQL statement. Now we are considering physical transactions in transactions and concurrency control, JDBC. The default for non-Jakarta persistent applications, the manages transaction via calls to java.sql.connection. Here which transaction coordinate builder implementation to use is defined by the Hibernate.transaction.coordinate underscore class settings. Now we are considering JTA configuration. Hibernate provides many implementation of the JTA platform contract with platform contract, all with short names. Here Atomicos, JTA platform for Atomicos. Now we are considering Hibernate transaction API. Here using transaction API in JDBC. Interface transaction represent a resource dash local transaction, where resource dash local is interpreted by Hibernate to mean any transaction under the control of Hibernate. That is to say, the underlying transaction might be a JTA transaction or it might be a JDBC transaction, depending on how Hibernate is configured. This is in the package org.hibernate. Hibernate provides an API for helping API to help isolate applications from the differences in the underlying physical transaction system in use. Based on the configured transaction coordinator builder, the Hibernate will simply do the right thing when this transaction API is used by the application. This allows your application and components to be more portable to move around into different environments. To use this API, you would obtain the org.hibernate.transaction from session. Transaction allows for all normal operations you would expect: begin, commit, and rollback. And it even exposes some cool methods like mark rollback only, that works in both JTA and JDBC, get timeout and set timeout, that again work on both JTA and JDBC, register synchronization, that allows you to register JTA synchronizations even in non-JTA environments. In fact, the both JTA and JDBC environment, these synchronizations are kept locally in Hibernate. In JTA environments, the Hibernate will only ever register one single synchronization with the transaction manager to avoid ordering problems. Additionally, it exposes get status methods that returns an org.hibernate.resource.transaction.spi.transaction status enum. This method check the underlying transaction. Here get status underlying transaction system if needed, so care should be taken to minimize its use. It can have a big performance impact in certain JTA setups. Let's take a look at running JTA API in various environments. Here using the transaction API in JDBC. JDBC is the default built for explicitness. Calls the connection hash set auto commit false to signal start of transaction. Calls the connection hash commit if an error happens. We attempt a rollback. We may need to roll back depending on where the exception happened. Handle the underlying error. Here using transaction API in JTA CMT. The interface transaction represent a source represent a resource dash local transaction where the resource dash local is interpreted by Hibernate to mean any transaction under control of Hibernate. That is to say, the underlying transaction might be a JTA transaction or it might be a JDBC transaction depending on how Hibernate is configured. This is in the package org.hibernate. Here in the CMT case, we really could have omitted all of the transaction calls, but the point of the example was to show that the transaction API really does insulate your code from the underlying transaction mechanism. In fact, if you strip away the comments and the single configuration settings applied at the bootstrap, code is exactly the same in the all three examples. In the other words, we could develop that code and drop it as is in any of the three transaction environments. JDBC is the default, but for explicitness. Note that depending on the JTA platform used and some optional settings, the underlying mechanism transactions here will be controlled through either JTA transaction manager or user transactions. Since we are in CMT, the JTA transaction would already have been started. This call essentially NOPs. Since we did not start the transaction CMT, we also will not end it. This call essentially NOPs in terms of transaction handling. Again, the rollback call here would be NOPs aside from marking the underlying CMT transaction for rollback only. Handle the underlying error. Now we are considering using transaction API in JTA BMT. The interface transaction represent a source dash local transaction where the source dash local is interpreted by Hibernate to mean any transaction under control of Hibernate. That is to say, underlying transaction might be a JTA transaction or it might be a JDBC transaction depending on how Hibernate is configured. This is in the package org.hibernate. The transaction API tries too hard to make the experience consistent across all environments. To that end, it generally refers to JTA specification when there are differences, for example, automatically trying to roll back a failed commit. JDBC is the default, but explicitness. Note, depending on the JTA platform used in and some optional settings, the underlying transaction here will be controlled through either the JTA transaction manager or user transaction. Assuming the JTA transaction is not already active, this call the TM UT begin method. If a JTA transaction is already active, we remember that the transaction associated with the session did not initiate the JTA transaction and will later NOP up the commit and rollback calls. calls tm ut commit method, assuming we are initiator. We may need to roll back the rollback depending on where the exception happens. Calls tmut commit method, assuming we are initiator, otherwise mark the JTA transaction for rollback only. Handling the underlying error. Now we are considering contextual sessions. Out of the box, Hibernate comes with 3 implementation of this interface. Here we are considering org.hibernate.context.internal.jta session context. Current sessions are tracked and scoped by a JTA transaction. The processing here is exactly the same as in the older JTA only approach. Other interfaces are org.hibernate.context.internal.thread local session context. Other one is org.hibernate.context.internal.message session context. Here the class JTA session context and implementation of current session context, which scopes the notion of a current session to a JTA transaction, because JTA gives us a nice tie-in to clean up after ourselves. This implementation will generate sessions as needed, provided JTA transaction is in effect. If a session is not already associated with the current JTA transaction at the time current session method is called, the new session is opened and is associated with the JTA transaction. This is in the package org.hibernate.context.internal. Now we are considering session per operation anti-pattern in transactional patterns and anti-patterns. This is an anti-pattern of opening and closing a session for each database call in a single thread. It is also an anti-pattern in terms of database transactions. Group of your database calls in a planned sequence. Group your database calls in a planned sequence. In the same way, you do not auto commit after every SQL statement into an application. Hibernate disables or expects the application server to disable auto commit mode immediately. Database transactions are never optional. All communication with the database must be encapsulated by a transaction. Avoid auto commit behavior for reading data because many small transactions are unlikely to perform better than one clearly defined unit of work and are more difficult to maintain and extend. Using autocommit does not circumvent database transaction. Instead, when in autocommit mode, the JDBC drivers simply perform each call in an explicit transaction call. It is as if your application called commit after each and every JDBC call. Now we are considering session per request pattern. There are 2 reliable defining scopes. The session get current session method throws hybrid exception. Here session get current session method obtains the current session, an instance of session explicitly associated with some context or scope. For example, the session might be associated with the current thread or with the current JTA transaction. This is in the package org.hibernate and it is in the interface SessionFactory. Public static session binds binds the given session to a current context for its session factory. This is in the class managed session context, which is in the package org.hibernate.context.internal. This is the most common transaction pattern. The term requests here relates to the concept of a system that reacts to a series of requests from the client server. Web applications are a prime example of this type of system, though certainly not the only one. At the beginning of handling such a request, the application opens a Hibernate session, starts the transaction, performs all related work, ends the transaction and closes the session. the crux of the pattern is one-to-one relationship between transaction and the session. Within this pattern, there is a common technique of defining current session to simply the need of passing this session around all the application components that may access to it. Hibernate provides support for this technique through getCurrentSession method of the SessionFactory. The concept of current session has to have a scope that defines the bound in which the notion of current is valid. This is the purpose of org.hibernate.currentText.spi.current-session-context contract. There are two reliable defining scopes. First is JTA transaction because it's allow a callback hook to know when it is ending, which gives Hibernate a chance to close the session and clean up. This is represented by a org.hibernate.context.internal.jta session context implementation of the org.hibernate.context.spi.current-session-context contract. Using this implementation, a session will be opened first time getCurrentContext is called within that transaction. Secondly, this application is request cycle itself. This is the best represented with the org.hibernate.context.internal.manage session context implementation of the org.hibernate.context.spi.current-session-context contract. Here, an external component is responsible for managing the lifecycle and scoping of a current session. At the start of such a scope, manage session context #bind method is called passing this in the session. In the end, its unbind method is called. Some common examples of such external components include javax.servlet.filter implementation, AOP interceptor with a point cut on service methods, a proxy interception container. The getCurrentSession method has one downside in a JTA environment. If you use it after _statement connection, release mode is also used by default. Due to the limitation of JTA specification, Hibernate cannot automatically clean up the close scrollable result or iterator instances returned by scroll method or iterate method. Release the underlying database cursor by calling scrollable result #close method or hibernate.close iterator explicitly from a finally block. Now we are considering automatic versioning in conversations, application level transactions. Hibernate can perform automatic optimistic concurrency control for you. It can automatically detect at the time of the app conversation if a concurrent modification occurred during user think time. Now we are considering session per application anti-pattern. The session per application is also considered, and one solution is to call clear and evict to manage the session cache, but you should consider a stored procedure if you need mass data operations. The method void clear completely clear the session, evict all loaded instances, and cancel all pending saves, updates, and deletions. Do not close open iterators and instances of scrollable results. Method void evict object. Remove this instance from the session cache. Changes to the instance will not be synchronized with the database. This operation cascade to associate instances if the association is mapped with cascade type detach. These are in this interface session, and which is in the package org.hibernate. Session per application is also considered an anti-pattern. The Hibernate session, like the Jakarta persistent entity manager, is not a thread-safe object, and it is intended to be confined in a single thread at once. If the session is sharing among multiple threads, there will be a race conditions as well as visibility issues, so beware of this. An exception is thrown by Hibernate means you have to roll back your database transaction and close the session immediately. If your session is bound to the application, you have to stop the application. Rolling back the application transaction does not put your business object back to the state where they were at the start of the transaction. This means that database state and business objects will be out of sync. Usually this is not a problem because exceptions are not recallable, but and you will have to start after rollback anyway. The session caches every object that is in the persistent state, washed and checked for dirty state by Hibernate. If you keep it open for a long time and simply load too much data, it will grow endlessly until you get out of memory exception. One solution is to call clear and evict to manage session cache, but you should consider a restart procedure if you need mass data operations. Some solutions are batching. Keeping a session open for a duration of the user session also means a higher portability of stale data. Now we are considering transaction statistics methods in org.hibernate.statistics method in statistics. Get successful transaction count, the number of transactions that completed successfully. The long get successful transaction count method, the number of transactions we know to have been successful. This is in the interface statistics and which is in the package org.hibernate.stat. Now we are considering transaction properties in configurations. Hibernate.transaction.jta.platform, for example, JBoss AS JBoss AS Bitronics JTA platform names the JTA platform implementation to use for integrating with JTA systems, can reference either a JTA platform instance or the name of the JTA platform implementation class. Now we are considering standard service registry in types of service registries in services and registries. Here the transaction coordinator builder. The org.hibernate.resource.transaction.spi.transaction coordinate builder is used by Hibernate to integrate with an underlying transaction system. It is responsible for building org.hibernate.resource.transaction.spi.transaction coordinator instances for used by each Hibernate session. The interface transaction coordinate builder in package org.hibernate.resource.transaction API. A transaction coordinator may be selected using the configuration property hibernate.transaction.coordinate_class. As an exception example, we can consider class transaction exception. Indicates that a transaction could not begin, committed or rollback. This class is in org.hibernate package. Now we are focusing on JNDI, the Java naming and directory interface. JNDI is a Java API for a directory service that allows Java software clients to discover and look up data and resources in the form of Java objects via a name. Like all Java APIs that interface with host systems, JNDI is independent of the underlying implementation. Additionally, it specifies a service provider interface SPI that allows directory service implementations to be plugged into the framework. The information looked up via JNDI may be supplied by a server, a flat file, or a database. The choice is up to the implementation used. Here you can see the architecture of JNDI. JNDI architecture consists of an API and a service provider interface SPI. Java applications use the JNDI API to access a variety of naming and directory services. The SPI enables a variety of naming and directory services to be plugged in transparently, thereby allowing the Java application using the JNDI API to access their services. The JNDI is included in the Java 2 SDK version 1.3 and later releases. It also available as a Java standard extension for use with the JDK 1.1 and the JDK and Java 2 SDK version 1.2. It extends the version 1.1 and version 1.2 platforms to provide segment. The line cfg.build SessionFactory still has to be executed somewhere to get a SessionFactory into JNDI in JMX deployment. You can do this either in a static initializer block like or you can deploy Hibernate as a managed service. Hibernate is distributed with org.hibernate.jmx.hibernate service for deployment on an application server with JMX capabilities such as JBoss AS. The actual deployment and configuration is vendor specific. Here is an example: JBoss dash service.xml for JBoss 4.0.x. This file is deployed in a directory called meta-inf and packaged in a jar file with the extension .sar service archive. You also need to package Hibernate, its required third-party libraries, your compiled persistent classes, as well as your mapping files in the same archive. Your enterprise beans, usually session beans, may be kept in their own jar file, but you may include this EJB jar file in the main service archive to get a single hot deployable unit. Consult the JBoss AS documentation for more information about JMX service and EGB deployment. Here you can see bind the Hibernate service to JNDI here. JNDI name and this one. This is jbox-service XML for jbox 4.0.x. As an example too, we can consider this. Here hibernate.connection.data source is data source JNDI name, and hibernate.jndi.url is URL of the JNDI provider, and hibernate.jndi.class class of the JNDI initial context factory. Hibernate.connection.username is database user, and hibernate.connection.password is database user password. Design the hibernate.properties file. Here we are considering package org.hibernate.engine.jndi, support for JNDI within Hibernate. Here you can see a hibernate.jndi.class. The standard JNDI service accepts a number of configuration settings. Here you can see hibernate.jndi.class in JNDI names the javax.naming.initial context implementation class to use, and interface JNDI service is in package org.hibernate.engine.jndi SPI. This is the service providing simplified access to JNDI related features needed by Hibernate. Now we are considering custom services in services and registries. Here custom service roles extending. Here event publishing service implementation. Here JNDI, the interface JNDI service in the package org.hibernate.engine.jndi.spi. Service providing simplified access to JNDI related features needed by Hibernate. We can also have service registry host custom services, completely new service roles. As an example, let's say our application publishes Hibernate events to an JMS topic, and that we want to leverage the Hibernate service registry to host a service representing our publishing of events. So we will expand service registry to host this completely new service role for us and manage its life cycle. Here event publishing service role here. Here event publishing service implementation. Here is an alternative event publishing service implementation. because we have alternative implementations, it's a good idea to develop an initiator as well that can choose between them at runtime. The event publishing service initiator here. We could have the application register the event publishing service initiator with the standard service registry builder, but it is much nicer to write service contributor to handle this for the application. Here nothing to do. If you wanted to allow other strategies, for example, a JMS queue publisher, we might also register short names here with the strategy selector. The initiator would then need to accept the strategy as a config setting. As an exception example, we can consider JNDI exception, an exception indicating trouble accessing JNDI. This class is in org.hibernate.engine.jndi package. As an error example, we can consider this not binding factory to JNDI, no JNDI name configured. Now we are focusing on JDBC, Java Database Connectivity. JDBC is an application programming interface API for the programming language Java, which defines how a client may access a database. It is a Java-based access technology used for Java database connectivity. It is part of the Java Standard Edition platform from Oracle Corporation. It provides methods to query and update data in a database and is oriented towards relational databases. A JDBC to ODBC bridge enables connections to any ODBC accessible data source in the Java Virtual Machine JVM host environment. Here you can see the role of JDBC. The most widely used interface to access relational database today is Microsoft ODBC API. ODBC performs similar tasks that of JDC, Java Development Connection, and yet JDBC is preferred due to following reasons. ODBC cannot be directly used with Java because it uses a C interface. Call from Java to native C code have a number of drawbacks in the security, implementation, robustness, and automatic portability of applications. ODBC makes use of pointers which have been totally removed from Java. ODBC mixes simple and advanced features together and has complex options for simple queries. But JDBC is designed to keep things simple while allowing advanced capabilities when required. JDBC API is a natural interface. It's a natural Java interface and is built on ODBC. JDBC contains some of the basic features of ODBC like XOpen, SQL call level interface. JDBC is to Java programs, and ODBC is to programs written in languages other than Java. ODBC is used between applications and JDBC is used by Java programmers to connect to databases. Here you can see Java application is connected to application interact with JDBC driver manager. Here you can see JDBC native bridge interacts with native driver DBMS specific. Native driver interacts with DBMS. Here JDBC ODBC bridge interacts with ODBC driver. ODBC driver interacts with DBMS. JDBC driver DBMS specific interacts with DBMS. JDBC middleware various DBMS interacts with DBMS. Here we can take this as an example. This is in the hibernate.properties file. Here you can see hibernate.connection.driver underscore class, JDBC driver class, hibernate.connection.url, JDBC URL, hibernate.connection.username, database user, hibernate.connection.password, database user password, Hibernate.connection.pool underscore size, maximum number of pooled connections. Here we are considering database connection settings. Here the connection, here database connection settings, connection.driver underscore class, JDBC driver class, connection dot URL, JDBC URL, connection dot username, database user, connection dot password, database user password. This is in hibernate.cfg.xml file. We are considering package org.hibernate.jdbc defines the notion of a unit of JDBC work that may be executed by the session at the request of the client. Here we are considering batching. Hibernate can leverage JDBC batching. This is one of the settings control this behavior. This Hibernate JDBC.batch underscore size controls the maximum number of statements Hibernate will batch together before asking the driver to execute the batch. 0 or a negative number disables this feature. JDBC offers support for batching together SQL statement that can be represented as a single prepared statement. Implementation wise, this generally means that drivers will send the batch operation to the server in one call, which can serve on network calls to the database. And Hibernate can leverage JDBC batching. This is one settings for control this behavior. Other settings are hibernate.jdbc.batch version data, hibernate.jdbc.batch.builder, hibernate.order underscore updates, hibernate.order insert, etc. Here you can see Hibernate specific JDBC batch size configuration on per session basis. Now we are considering JDBC statistics methods in org.hibernate.stat.statistics methods in statistics. Get prepared statement count, the number of JDBC prepared statements that were acquired by Hibernate. Long get prepared statement count method, the number of prepared statements that were acquired. This is in the interface statistics, which is in the package org.hibernate.stat. Now we are considering JDBC related options in mapping properties in configuration. Here hibernate.use underscore nationalize underscore character underscore data. For example, true or false default value. Enable nationalize character support on all string or club based attribute, string, char, club, text, etc. Now we are considering at any key JDBC type in Hibernate annotations in mapping annotations. The at any key JDBC type annotation specifies a specific JDBC type crypto to use for a foreign key of any mapping. This is in the annotation type any key JDBC type form of JDBC type used to target the foreign key part of any mapping. This is in the package org.hibernate.annotations. at any key JDBC type code. The at any key JDBC type code annotation specifies the type code indicating which JDBC type crypto JDBC type descriptor to use for the foreign key of any mapping. This is in the this annotation type any key JDBC type code form of JDBC type code used to describe the foreign key part of any mapping. This is in the package org.hibernate.annotations. Now we are considering JDBC batching in performance tuning and best practices. Not only insert and update statements, but even delete statement can be batched as well. JDBC allows us to batch in multiple SQL statements and send them to database server in a single request. This saves the database round trips and also reduces response time significantly. Not only insert and update statement, but even delete statement can be batched as well. For insert and update statement, make sure that you have all right configuration properties in place, like ordering insert, updates, and activating batching for versions data. For delete statements, there is no option to order parent and child statements, so cascading can interfere the JDBC batching process. Unlike any other framework which doesn't automate SQL statement generation, Hibernate makes it very easy to activate JDBC level batching. An exception example, we can consider JDBC exception, wraps and SQL exception indicates that an exception occurred during a JDBC call. This class is in org.hibernate package. As an error example, we can consider this JDBC exception on Hibernate data access, SQL exception for SQL state XX000 error code 0 could not extract result set. Nested exception is org.hibernate.exception.generic JDBC exception could not extract result set. This happened in JDBC exception on Hibernate data access. Now we are focusing on JTA, the Jakarta transactions. JTA, formerly Java Transaction API, one of the Jakarta EE APIs, enables distributed transactions to be done across multiple open XA resources in a Java environment. JTA was a specification developed on the Java community process as JSR 907. JTA provides for demarcation of transactions boundaries. Open XA API allowing resources to participate in transactions. Here you can see distributed transactions and the transaction manager. A distributed transaction is a transaction that accesses and updates data on two or more networked resources. These resources could consist of several different RDBMS housed on a single server, for example Oracle SQL Server and Sybase, or they could include several instances of a single type of database residing on a number of different servers. In any case, a distributed transaction involves coordination among the various resource managers. This coordination is the function of the transaction manager. The transaction manager is responsible for making the final decision either to commit or roll back any distributed transaction. A commit decision should lead to a successful transaction. Rollback leaves the data in the database unaltered. JTA specifies standard Java interface between the transaction manager and the other components in the distributed transaction, the application server, and the resource managers. This relationship is illustrated in this diagram. The numbered boxes around the transaction manager correspond to the three interface portions of JTA. 1. User transaction. The javax.transaction.userTransaction interface provides the application the ability to control transaction boundaries programmatically. The javax.transaction.userTransaction method starts a global transaction and associate the transaction with the calling thread. The two transaction manager. The javax.transaction.transaction manager interface allow the application server to control transaction boundaries on behalf of the application being managed. Number 3, XA resource. The java.transaction.xa.xa resource interface is a Java mapping of the industry standard XA interface based on the XOpen CAE specification, distributed transaction processing, the Java XA specification. Notice that the critical link is support of the XA resource interface by the JDBC driver. The JDBC driver must support both normal JDBC interactions through the application or the application server, as well as the XA resource portion of JTA. Data Direct Connect for JDBC drivers provide the support. Developers of code at the application level should not be concerned about the details of distribution transaction management. This is the job of the distributed transaction infrastructure, the application server, the transaction manager, and the JDBC driver. The only caveat for application code is that it should not invoke method that would affect boundaries of the transaction while the connection is the scope of distributed transaction. Specifically, an application should not call the connection methods commit, rollback, and set auto commit true because they would interfere with the infrastructure's management of the distributed transaction. Here you can see in JTA Java application is here, and application service here below, JDBC driver manager is there, and below that JDBC driver, and is and JTA connected to the database here. And the Java application is connected to transaction manager and JTA here. The one is user transaction, and 2 is transaction manager, and 3 is XA resource. We can consider this one as an example, JBoss transaction. The segment is in persistent.xml file. Here you can see a name attribute. Every entity manager must have a name, and transaction type attribute, transaction type used either JTA or resource underscore local, default to JTA in an EE environment, and to resource underscore local in a Java SE environment. When this is when JTA dash data source is used, the default is JTA. If none dash JTA dash data source is used, resource underscore local is used. JTA and dash data dash source or none dash JTA dash data dash source. This is the JNDI name of where the javax.sql data source is located. If we use the SQL when running without a JNDI available data source, you must specify JDBC connection with Hibernate specific properties. Properties. The properties element is used to specify vendor specific properties. This is where you will define your Hibernate specific configurations. This is also where you will have to specify JDBC connection information as well. As an example too, we can consider this one. Here name attribute, every entity manager must have a name. Transaction type attribute, transaction type used either JTA or resource underscore local, default to JTA in a Java EE environment, and to resource underscore local in a Java SE environment. When a JTA dash data source is used, the default is JTA. If none dash JTA dash data source is used, resource underscore local is used. And concurrency control. Hibernate provide many implementation of the JTA platform contract with short names. Here, for example, Boland, JTA platform for the Boland enterprise server. Now we are considering JTA platform in standard service registry, in types of service registries, in services and registries in Hibernate ORM 6.2 integration guide. JTA platform, when using a JTA based transaction coordinate builder, the org.hibernate.engine.transaction JTA.platform SPI.JTA platform service provides Hibernate access to the JTA transaction manager and transaction, as well handling synchronization registration. The interface JTA platform, which is in package org.hibernate.engine.transaction.jta.platform.spi, a service that defines how Hibernate interact with JTA on a certain platform. In particular, a JTA platform allows Hibernate to obtain the transaction manager and user transaction and register synchronizations. Except as an exception example, you can consider JTA platform inaccessible exception. Indicates problems accessing transaction manager or user transaction through the JTA platform. This exception is in this class is in org.hibernate.resource.transaction.backend.jta.internal package. As an error example, we can consider could not register synchronization with JTA transaction manager here. Now we are focusing on database. Database, also called electronic database, any collection of data or information that is specially organized for rapid search and retrieval by a computer. Databases are structured to facilitate the storage, retrieval, modification, and deletion of data in conjunction with various data processing operations. A database management system, DBMS, extracts information from the database in response to queries. Here you can see how Hibernate works. At the heart of every interaction between your code and the database lies the Hibernate session. The heart of any Hibernate application is in its configuration. There are two pieces of configuration required in any Hibernate application. One to create the database connection, and the other creates the object to table mapping. Here you can see .cfg.xml. This file is connected to Hibernate configuration for database 1. Loaded to create is passed from .cfg.xml file to Hibernate configuration data for database 1. Hibernate configuration for database 1 is connected to database 1. And here .cfg.xml is connected to class.class1.hmb.xml and other similar files. Here defines the database specific settings and groups, HBMs for a given database. .cfg.xml is connected to Hibernate configuration for database 2, and loaded to create is passed from .cfg to .cfg.xml to Hibernate configuration for database 2, and Hibernate configuration for database 2 is connected to database 2, and here work with multiple databases. And Hibernate configuration for database 2 is connected to factory, and configuration object is used to create here, and single factory is singleton per database, and factory is connected to session, and there's a bridge between among tables and classes and session. Here you can see Hibernate ORM and Hibernate OGM. if you take MongoDB as NoSQL database here, MongoDB does not require following ACID properties and hence do not support the transaction. Hibernate OGM mitigate its lacking by queuing changes before committing them. Hibernate OGM also recommends using in transaction demarcation with no rollback option. Perhaps this is the reason why bootstrapping through JTA is suggested. Because of JPA is an inherently relational API, so be prepared for you to run into these aspects. First, JPA is not supporting a plethora of the features MongoDB exposes: geopartial functionality, upserts, etc. You are going to need a custom extension for that, in which minimizes the benefit of using JPA in the first place. And number two, a plethora of stuff available in JPA doesn't make any sense in MongoDB non-relational world and won't be supported. Transactions, what's a join column supports supposed to be in MongoDB. The former not bring available a pretty dangerous actually. What's supposed to happen if a JPA developer calls transaction.rollback? Strictly speaking, you can't implement JPA 100% by definition, and most of the self-proclaimed JPA implementations for NoSQL are basically providing a tiny subset of JPA. Some of the annotations for mapping some of the entity managed API. And number three, simply switching the store behind an object model is fallacy to, especially NoSQL stores are built in a way to favor certain data structures. MongoDB is good for documents. Neo4j is highly interconnected data. That means that you will model the domain code and the converters differently based on what you store you actually use. Switching stores arbitrarily will lead you to reduce your domain model to a least common denominator and basically make less use of the features that might you select the store in the first place. Here you can see Hibernate ORM here, and application, then Hibernate ORM, then JNDI, JDBC layer, JTA, and these are interact with the SQL database, and SQL statements are passed to SQL database and results from SQL database. Here you can see Hibernate OGM application, Hibernate ORM, Hibernate OGM, data store provider, grid dialect, and these are interacting with NoSQL database. Here you can see the general architecture of Hibernate OGM. Hibernate OGM is really made possible by the reuse of a few key components. Hibernate ORM for JPA support, Hibernate's search for indexing and query purposes, the NoSQL drivers to interact with underlying data store, Infinispan's losing directory to store indexes in Infinispan itself or in many other NoSQL using Infinispans right through cache stores, Hibernate OGM itself. Hibernate OGM reuses as much as possible from Hibernate ORM infrastructure. There's no need to rewrite an entirely new JPA engine. Persisters and loaders two interfaces used by Hibernate ORM have been rewritten to persist data in the NoSQL store. This implementation are the core of Hibernate OGM. The particulars between NoSQL stores are abstracted by the notion of data store provider and data grid. Data store provider abstracts how to start and maintain a connection between Hibernate OGM and the data store. Grid dialect abstract how itself, including association, is persisted. Other than these, all the create, read, update, delete, CRUD operations are implemented by the Hibernate ORM engine. Object hydration and dehydration, cascading, lifecycle, etc. As if today 4 data store providers are implemented: a map based data store provider for testing, an Infinispan based data store provider for persist your entities in Infinispan, Ncache based data store provider to persist your entities in Ncache, a MongoDB based data store provider to persist data in a MongoDB database. To implement JPQL queries, Hibernate OGM parses the JPQL string and calls the appropriate translator functions. To build a native query. If the query is too complex, the native capabilities of the NoSQL store, the TIED query engine is used as the an intermediary engine to implement the missing features, typically joins between entities aggregation. Finally, if the underlying engine does not have any query support, Hibernate Search is used as an external query engine. Hibernate OGM best work in a JTA environment. The easiest solution is to deploy it on a Java EE container. Alternatively, you can use a standalone JTA transaction manager. Here you can see application. Object model is inside the application, and application is connected to JPA or Hibernate native APIs, and it's interact with JPA or Hibernate native APIs. JPA or Hibernate native API, Hibernate core, Hibernate ORM core, Hibernate OGM core, data store provider, and grid dialect query engine are in Hibernate OGM. JPA or Hibernate native APIs are connected to Hibernate ORM core. Basically, they are interacting with ORM, Hibernate ORM core, and Hibernate ORM core is connected to Hibernate OGM core. Delegates persistence load queries to Hibernate OGM core. Hibernate OGM core delegates data store CRUD operations to data store provider and grid dialect. Data store provider and grid dialect interacts with data store here with NoSQL data store. Hibernate OGM core delegates queries to JPQL parser. JPQL parser, data store query translator, and tied query engine and connectors are inside query engine. And JPQL parser delegates simple queries to data store query translator. JPQL parser delegates complex queries to tied query engine and connectors. Tied query engine and connectors transform in a simpler data store supported queries to data store query translator. Data store query translator executes native queries and it is connected to SQL data store. Here you can see a separate database in multi-tenant approaches. Each tenant data is kept in a physically separate database instance. JDBC connection would point which point specifically to each database. So any point would be per tenant. A general application approach here would be to define a JDBC connection pool per tenant and to select the pool to use based on the tenant identifier associated with the currently logged in user. Here you can see application is connected to databases. Here you can see a separate schema in multi-tenant approaches. Each tenant data is kept in a distinct database schema. There are two different ways to define JDBC connections here. Connection could point to specifically to each schema as we show in the separate database approach. This is an option provided that the driver supports naming distinct default schema in the connection URL or if the pooling mechanism supports the naming schema for use its connections. Using this approach, we would have a distinct JDBC connection pool per tenant, where the pool to use would be selected based on the tenant identifier associated with the currently logged in user. Connections could point to database itself using the default schema, but the connections would be altered using SQL set schema or similar command. Using this approach, we would have a single JDBC connection pool for use to service all tenants, but before using connection it would be altered to reference schema name the current tenant identifier associated with the currently logged user. Here you can see application is connected to databases. Partition discriminator data in multi-tenant data approaches. The all data is kept in a single database schema. The data for each tenant is partitioned by the use of partition value or discriminator. The complexity of this discriminator might range from simple column value to a complex SQL formula. Again, this approach would use a single connection pool service to all tenants. However, in this approach, the application needs to alter each and every SQL statement to send to database to reference the tenant identifier discriminator. Here, application is connected to the database. As an example, we can configure the database connection. This segment is from hibernate.csv.xml. To create a connection to a database, Hibernate must know the details of our database tables, classes, and other mechanics. This information is ideally provided as XML file, usually named hibernate.cfg.xml, or as a simple text file with name value pairs, usually named hibernate.properties. Here connection URL indicates the URL to which we should be connected, and driver underscore class represent the relevant driver class to make the connection, and dialect indicates which database dialect we are using, MySQL in this case, and if you are following the hibernate.properties file approach, note that all the properties are prefixed with hibernate and follow pattern hibernate asterisk properties, for instance. We can consider this one as example 2 for Hibernate OGM. This is in persistent.xml. So here we have to define data store details in a Hibernate persistent.xml. The value of the attribute transaction-type as an JTA. This implies that we want a JTA entity manager from the entity manager factory, and provider, which is Hibernate OGM persistence for Hibernate OGM. Additional details related to DB. These typically vary between different data sources. The configuration assumes MongoDB is running and accessible on defaults. If this is not the case, we can always provide details as necessary. And as an example 3, we can consider this one in hibernate.properties file. Here hibernate.connection.ur indicates the URL to which we should be connected. Driver class represents the relevant driver class to make a connection, and the dialect indicates which database dialect we are using, MySQL in this case. If you are following the hibernate.properties file approach, note that all the properties are prefixed with hibernate and follow a pattern hibernate.properties, for instance. As an example 4, we can consider this code segment. Here the class configuration. An instance of a configuration allows the application to specify properties and mapping documents to be used when creating a SessionFactory. Usually an application will create a single configuration, build a single instance of SessionFactory, and then instantiate sessions in a thread servicing client requests. The configuration is meant only as a initialization time object. SessionFactories are immutable and do not retain any association back to the configuration. The class configuration is in org.hibernate.cfg as an exception. Now we are considering columns index. Here is at index mapping example. The at index annotation is used by the automated schema generation tool to create a database index. Considering the following entity mapping, Hibernate generates the index when creating a database schema. Getter and setters omitted for brevity. Now we are considering connection provider in database access. Hibernate will internally determine which connection provider to use based on the following diagram. Interface connection provider in package org.hibernate.engine.jdbc.connection.spi, a contract for obtaining JDBC connections and optionally for pooling connections. As an ORM tool, probably the single most important thing you need to tell Hibernate is how to connect to a database so that it may connect on behalf of your application. This is ultimately the function of the org.hibernate.engine.jdbc.connection.spi.connection provider interface. Hibernate provides some out-of-box implementation of this interface. Connection provider is also an extension point, so you can also use the custom implementation from third parties or written yourself. The connection provider is used to provider to use is defined by the hibernate.connection.connectionProvider_class setting. Generally speaking, applications should not have to configure the connection provider explicitly if using one of the Hibernate provided implementation. Hibernate will internally determine which connection provider to use based on the following algorithm. 1. If Hibernate connection provider class is set, it takes precedence. 2. Else if Hibernate.connection.dataSource is set using data sources. 3. Else if any settings prefixed by Hibernate.3cp0 is set using 3c3p0. 4. Else if any setting prefixed by Hibernate.procsol is set using procsol. 5. Else if any setting prefixed by Hibernate.hikari is set using hikari cp. 6. Else if any setting prefixed by Hibernate.vibu is set using vibu.dbcp. Else if any settings prefixed by Hibernate.agrol is set using agrol. Else if Hibernate.connection.url is set using Hibernate's built-in and unsupported pooling. Else user provided connections. Now we are considering using data sources. Hibernate can integrate with javax.sql.datasource for obtaining JDBC connections. Application would tell Hibernate about the data source via the required Hibernate.connection.datasource settings, which can either specify a JNDI name or would reference an actual data source instance. For Jakarta persistent applications, note that Hibernate.connection.datasource corresponds to Jakarta.persistence.jta datasource or Jakarta.persistence.none.jta datasource. The data source connections, the data source connection provider also optionally accepts the hibernate.connection.username and hibernate.connection.password. If specified, the data source hash get connection string username string password will be used. Otherwise, no args form is used. Now we are considering driver configuration. Here, hibernate.connection.driver_class, the name of the JDBC driver class to use. Here we are considering using C3P0 C3P0.minsize or C3P0.minpoolsize, the minimum size of the C3P0 pool. Now we are considering using existing Proxol pools in using Proxol controlled by the hibernate.proxol.existing_pool setting. If set to true, this connection provider will use the already existing Proxol pool by alias as indicated by the hibernate.proxol.pool_alias settings. Now we are considering using Hikari CP hibernate.connection.driver_class map to Hikari's driver class name setting. Now we are considering using Vibu DBCP hibernate.connection.driver_class map to Vibu's driver class name setting. Now we are considering using a role hibernate.connection.driver_class map to a role's driver class name setting. And now we are considering using Hibernate's built-in and unsupported pooling. The built-in connection pool is not supported for use in production and systems. So now we are considering user-provided connections. It is possible to use Hibernate by simply passing a connection to use to the session when the session is open. This usage is discouraged and not discussed here. Now we are considering connection provider support for transaction isolation setting. The value for hibernate.connection.isolation can be specified in one of three formats. All of the provided connection provider implementations other than data source connection provider support consistent settings of transaction isolation for all connections. The connections obtained from the underlying pool. The value for hibernate.connection.isolation can be specified in one of three formats. The integer value accepted at the JDBC level. The name of the java.sql.connection constant field representing the isolation you would like to use. For example, transaction_repeatable_read for java.sql.connection hash transaction_repeatable_read. Note that this is only supported for JDBC standard isolation level, not for isolation level specific to a particular JDBC driver. A short name version of the java.sql.connection constant field without the transaction_prefix. For example, repeatable_read for java.sql.connection hash transaction_repeatable_read. Again, this is only supported for JDBC standard isolation levels, not for isolation level specific to particular JDBC driver. Now we are considering connection handling. Here immediate acquisition _and_hold. The connection will be acquired as soon as the session is opened and held until the session is closed. The enum constant public static final physical connection handling mode immediate acquisition _and_hold. The connection will be acquired as soon as the session is opened and held until the session is closed. This is the only valid combination including immediate acquisition of the connection. This is in the package connection and This is in the enum physical connection handling mode. Enumerates valid combination of connection acquisition mode and connection release mode, which is the enum is in package octahibernate.resource.jdbc.spi. There are other strategies like delayed acquisition and hold, delayed acquisition and release after statement, delayed acquisition and release after transaction. Now we are considering user provided connections. If the current session was created using the session builder and the JDBC connection was provided via the session builder hash connection method, then the user provided connection is going to be used, and the connection handling mode will be immediate underscore acquisition underscore and underscore hold. The method session builder connection adds a specific connection to the session points. This is in the interface session builder, and which is in the package org.hibernate. And therefore, for the user provided connection, the connection is acquired right away and held until the current session is closed without being influenced by the Jakarta persistence or Hibernate transaction context. Now we are considering database dialect. Here you can see cache 71 support for the cache database version 2007.1. For some reason it is not able to determine proper one, or for you want to use a custom dialect, you will need to set the hibernate.dialect settings for change set the dialects. Here we are considering dialect cache 71, and with regarding class dialect represent a dialect of SQL implemented by a particular RDBMS. Every class of this class implements support for the certain dialect database platform. For example, PostgreSQL dialect implements support for PostgreSQL, and MySQL dialect implements support for MySQL. The class dialect is in package org.hibernate.dialect. Now we are considering overview in Spatial. Supported databases are Oracle 10G, 11G, Postgres, SQL, PostgreSQL, MySQL, Microsoft SQL Server, DB2, Cockroach DB, and H2 or GeoDB. The Hibernate Spatial was originally developed as a generic extension to Hibernate for handling geographic data. Since 5.0, Hibernate Spatial is now part of the Hibernate ORM project, and it allows you to deal with geometric data in standardized way. Hibernate Spatial provides a standardized cross-database interface to geometric data storage and query functions. It supports most of the functions described by the OGC in simple feature specification. Supported databases are Oracle 10G, 11G, PostgreSQL, PostGIS, MySQL, Microsoft SQL Server, DB2, Cockroach DB, and H2 or GeoDB. Spatial data types are not part of Java standard library, and they are absent from JDBC specification. Over the years, JTS has emerged as a de facto standard to fill this gap. JTS is an implementation of simple feature specification, SFS. Many databases, on the other hand, implement the SQL hash or part 3 spatial data specification, related but border specification. The biggest difference is SFS is limited to 2D geometries in the projected pane, although GTS support 3D coordinates, where SQL or support 2, 3 or 4 dimensional coordinate spaces. Hibernate Spatial supports two different geometric modes, JTS and GeoLet GOM. As already mentioned, JTS is the de facto standard, and GeoLet GOM, also written by lead developer of Hibernate Spatial, is more recent library that support many features specified in SQL or but not available in JTS, such as support for 4D geometries and support for extended WKT or WKB formats. GeoLet, Geom also implement encoders, decoders or for the database native types. GeoLet Geom has good interoperability with JTS, converting a GeoLet geometry to a JTS geometry, for instance, doesn't require copying of coordinates. It also delegates spatial processing of JTS. Whether you use JTS or GeoLet Geom, Hibernate spatial maps the database spatial types to your geometry model of choice. It will, however, always use GeoLet Geom to decode the database native types. Hibernate spatial also make the number of spatial functions available in SQL and in the criteria query API. These functions are specified in the both SQL and or as SFS and are commonly implemented in the database with spatial support. Now we are considering dependency in configuration. Here Maven dependency. You need to include Hibernate hash spatial dependency to your build environment. For Maven you need to add following dependency. Note that all databases support all functions defined by not all databases support all functions defined by Hibernate spatial. The table now we are considering DB2 in database nodes. One way to do is to copy this statement into a file such as ewkt.sql and execute it in the db2 command window with the command such as db2-tvf ewkt.sql. The db spatial dialect supports the spatial extension of db2 LUW database. The dialect has been tested with db2 LUW 11.1. The dialect does not support db2 for Z or OS or db2 column oriented databases. In order to use db2 Hibernate spatial capabilities, it is necessary to first execute the following SQL statement, which will allow db2 to accept extended well-known text ewkt data and return ewkt data. The one way to do is to copy these statements into a file such as ewkt.sql and execute it in the db2 command window with a command such as db2 -tvf ewkt.sql. Now we are considering types. Here types mapping. Hibernate special comes with different types. It's sufficient to declare the property as either JTS or uh, geometry, and Hibernate partial will map it using relevant type. Here is the example using JTS. Now we can now treat spatial geometries like any other type. Here's creating a point. Special dialects define many query functions that are available in both HQL and JPQL queries. Below we show how we could use the within function to find all the objects within a given spatial extent or window. Getters and setters are omitted for brevity. Now we are considering multi-tenancy. What is multi-tenancy? The term multi-tenancy is applied to software development to indicate an architecture in which a single running instance of an application simultaneously serves multiple client tenants. This is highly common in SaaS solutions, isolating information, data, customizations, etc. pertaining to various tenants is a particular challenge in these systems. This includes the data owned by each tenant stored in the database. It is this last piece, sometimes called multi-tenant data, that we will focus on. Now we are considering multi-tenancy in Hibernate, specifying tenant here, specifying tenant identifier from a SessionFactory. Method session builder dot tenant identifier string tenant identifier define the tenant identified to be associated with the open session. This is in the interface session builder, which is in the package org.hibernate. Using Hibernate with multi-tenant data comes down to both an API and then integration pieces. As usual, Hibernate strives to keep the API simple and isolated from any underlying integration complexities. The API is really just defined by passing the tenant identifier as part of the opening and session. Now we are considering at tenant ID. At tenant ID usage example is here. The annotation type tenant ID identifies a field of an entity that holds a tenant ID in a discriminator based multi-tenancy. This is in the package org.hibernate.annotations. For the partition data approach, for each entity representing partitioned data must declare a field annotated with a tenant ID. The tenant ID field is automatically populated by Hibernate when an instance is made persistent. Now we are considering a multi-tenant connection provider. A multi-tenant connection provider implementation here. The multi-tenant connection provider, interface multi-tenant connection provider, a specialized connection provider contract used when the application is using multi-tenancy support requiring tenant-aware connections. The interface multi-tenant connection provider is in package org.hibernate.engine.jdbc.connection.spi. The abstract multi-tenant connection provider class, the basic support for multi-tenant connection provider implementation using individual connection provider instances per tenant behind the scene. When using either a separate database or separate schema approach, Hibernate needs to be able to obtain connections in a tenant specific manner. That is the role of multi-tenant connection provider. Multi-tenant connection provider contract. Application developers will need to provide an implementation of this contract. Most of the methods are extremely self-explanatory. Only ones which might not be get any connection and release any connection. It is important to note that that these methods do not accept tenant identifier. Hibernate uses these methods during startup to perform various configuration, mainly via SQL, java.sql.database metadata object. The multi-tenant connection provider to use can be specified in a number of ways. Use the hibernate.multi-tenant multi_tenant_connection_provider setting. It could name multi-tenant connection provider instance, a multi-tenant connection provider implementation class reference to a multi-tenant connection provider implementation class name. Pass directly to org.hibernate.boot.registry.standard service registry If none of above options match, but the settings do specify hibernate.connection.data source value, Hibernate will assume it should use the specific data source based multi-tenant connection provider IMPL implementation, which works on a number of pretty reasonable assumptions when running inside an app server and using one java x.sql.data source per tenant. The following example portrait multi-tenant connection provider implementation that handle multiple connections, handle multiple connection providers. The multi-tenant connection provider implementation is here. For the configurable multi-tenant connection provider can be set up as follows. Multi-tenant connection provider usage example. Here a multi-tenant connection provider usage example. When using multi-tenancy, it's possible to save an entity with same identifier across different tenants. Now we are considering current tenant identifier resolver. There is two situations where the current tenant identifier resolver is used. Interface current tenant identifier resolver in package org.hibernate.context.spi. A callback registered with the session factory that is responsible for resolving the current tenant identifier. The org.hibernate.context.spi.current session identifier resolver is a contract for Hibernate to be able to resolve with what the application considers the current tenant identifier. The implementation to use can be either passed directly to configuration via its set current tenant identifier resolver method, or be specified via hibernate.tenant_identifier_resolver setting. There are two situations where current tenant identifier resolver is used. First situation is when the application is used the org.hibernate.context.spi.current session context feature in the conjunction with multi-tenancy. In the case of the current session feature, Hibernate will need to open a session if it cannot find the existing one in scope. However, when a session is opened, the multi-tenancy environment, the tenant identifier has to be specified. This is where the current tenant identifier resolver comes into play. Hibernate will consult the implementation you provide to determine the tenancy identifier to use when opening the session. In this case, it is required that a current tenant identifier resolver is supplied. The other situation is when you do not want to explicitly specify the tenant identifier all the time. If the current tenant identifier resolver has been specified, the Hibernate will use it to determine the default tenant identifier to use when opening the session. Additionally, the current tenant identifier resolver implementation returns true for its validate existing current sessions method. Hibernate will make sure any existing sessions that are found in the scope have a matching tenant identifier. This capability is only pertinent when the current tenant identifier resolver is used in current tenant settings. Now we are considering caching. Multi-tenancy support for Hibernate works seamlessly with the Hibernate second level cache. The key used to cache data encodes the tenant identifier. Currently, the schema will export. The schema export will not really work with multi-tenancy. Now we are considering multi-tenancy Hibernate session configuration. The register connection provider method. The register connection provider method used to defining the tenant specific context. When using multi-tenancy, you might want to configure each tenant specific session differently. For instance, each tenant could specify different time zone configuration. Here they are registering the tenant specific time zone information. The register connection provider method is used to define the tenant specific context. In our example, the tenant specific context is held in the connection provider map and time zone tenant map. Now when building hybrid session, aside passing the tenant identifier, we could also configure the session to use the tenant specific time zone. Here the hybrid session can be configured using tenant specific context. So if we set the use tenant time zone parameter to true, Hibernate will persist the timestamp properties used in tenant specific time zone. As you can see the following example here, timestamp is successfully retrieved even if the currently running JVM uses different time zone. However, behind the scene, we can see that Hibernate has saved the create on property in the tenant specific time zone. Following example shows that timestamp was saved in the UTC time zone, hence offset displayed in the test output. Here with the use tenant time zone, property to set to false if the timestamp is fetched in the tenant specific time zone. Notice that for Eastern European time zone is the time zone offset was 2 hours when the test was executed. Here the persisting part, now we are considering portability basics in database portability considerations. One of the selling point of Hibernate and really object relational mapping as a whole is the notion of database portability. This could mean an internal IT user migrating from one database vendor to another, or it could mean a framework for deployable application consuming Hibernate to simultaneously target multiple products by their users. Regardless of the exact scenario, the basic idea is that you want Hibernate to help to run you against any database, any number of databases without changes to your code, ideally without any changes to the mapping data metadata. Now we are considering dialect, the org.hibernate.dialect.dialect. The first line of portability for Hibernate is the dialect, which is specialization of the org.hibernate.dialect.dialect contract. A class dialect represent the dialect of SQL implemented by a particular RDBMS. Every subclass of this class implements support for a certain database platform. For example, PostgreSQL dialect implements support for PostgreSQL and MySQL dialect implements the support for MySQL. A dialect encapsulate all the differences in how Hibernate must communicate with the particular database to accomplish some task, like getting a sequence value for constructing for structuring a select query. Hibernate bundles a wide range of dialects for many of the popular databases. If you find that your particular database is not among them, it is not terribly difficult to write your own. Now we are considering dialect resolution. Starting with version 3.3, Hibernate has far more powerful way to automatically determine which dialect to be used by relying on a series of delegates which implement the org.hibernate.dialect.resolver.dialect.resolver, which define only a single method. Originally, Hibernate would always require that users specify which dialect to use. In the case of users looking at the simultaneously target multiple databases with their build, that was problematic. Generally, this required the users to configure the Hibernate dialect or defining their own method of setting that value. Starting with version 3.2, Hibernate introduced a notion of automatically detecting the dialect to use based on the java.sql.database metadata obtained from the java.sql.connection to that database. This was much better, except that the resolution was limited to databases Hibernate know about ahead of time and was in no way configurable or overridable. Starting with version 3.3, Hibernate has far more powerful way to automatically determine which dialect to be used by relying on series of delegates which implement the org.hibernate.dialect.resolver.dialect.resolver, which defines only one single method. Basic contract here is that the resolver understands the given database metadata when it returns the corresponding dialect. If it's not returned null, if not, it returns null and process continues to the next resolver. Signature also identified the Hibernate.exception.JDBC connection exception as possibly being thrown. The connection exception here is interpreted to imply a non-transient, also known as non-recoverable connection problem, and is used to indicate an immediate stop to resolution attempts. All other exceptions result in warning and continuing on the next resolver. The cool part of these resolvers is that users can also register their own custom resolvers which will be processed ahead of built-in Hibernate ones. This might be useful in a number of different situations. It allows easy integration for auto detection of dialects beyond those shipped with Hibernate itself. It allows you to specify to use the custom dialect when a particular database is recognized. To register one or more resolvers, simply specify them separated by commands, tabs or spaces using Hibernate.dialect_resolvers configuration settings. Now we are considering identifier generation. There are specifically two bundled enhanced generators. The class sequence style generator in package org.hibernate.id.enhance generates identifier values based on a sequence style database structure. Variations range from actually using a sequence to using a table to mimic a sequence. These variations are encapsulated by the database structure interface internally. When considering portability between databases, another important decision is selecting the identifier generation strategy you want to use. Originally, the Hibernate provided a native generator for this purpose, which was intended to select between sequence, identity, or table strategy depending on the capability of underlying database. However, insidious implication of this approach comes when they're targeting some databases which support identity generation in some which do not. Identity generation relies on this SQL definition of an identity or auto increment column to manage the identifier value. It is what is known as the post insertion generation strategy, because the insert must actually happen before we know the identifier value, because Hibernate relies on this identifier value to uniquely reference entities within a persistent context. It must then issue the insert immediately when the user requests that identity be associated with the session, like via save or persist, regardless of the current transaction semantics. Hibernate was changed slightly once implications of this were better understood. So now insert could be delayed in cases where this is feasible. The underlying issue is that the actual semantics of the application itself changes these cases. Starting with version 3.2.3, Hibernate comes with a set of enhanced identifier generators targeting portability in which much different way. This specifically bundled with enhanced generator org.hibernate.id.enhance.identity is a sequence style generator, and other one is org.hibernate.id.enhance.table generator. The idea behind these generators is to port the actual semantics of the identifier value generation to the different databases. For example, org.hibernate.id.enhance.sequence style generator mimics this behavior of a sequence on databases which do not support sequence by using a table. Now we are considering database functions. There are even way for a program to contribute its own function definition. Here type, the function type applied to an identification variable, evaluates to the identity name of the reference entity. This is mainly useful when dealing with entity inheritance hierarchies. SQL now provide a large set of functions which are portable between databases. Using parameter instead of literal entity type. Now we are considering database connection properties in configurations. Here hibernate.connection.driver_class or jakarta.persistent.jdbc.driver, for example, log.postgresql.driver names the JDBC driver class name. Now we are considering Hibernate internal connection pool options. Hibernate.connection.initial_pool_size, for example, one default value, minimum number of connections for the built-in Hibernate connection pool. Well, we can consider this caused by java.sql exception ORA-12899 value too large for column JBPM dot case fields dialog dot item value. As an error example, we can consider this could not get list of tables from database, probably a JDBC driver problem. This is the end of my presentation. Thank you very much for watching it.